So we got that up and going, and you're just going over the ground. So what's problem number one? If
a squared and the sequence of a squared n converges, then an also converges.
All right, wonderful. So just because some sequence squared converges, does that necessarily mean that the sequence itself converges? And the answer is no, and Jacob's going to give us an example of one where it's not true. False. If a to the n equals -1, then a to the n equal to -1 converges. So try again. You're trying to find an an squared that converges where an doesn't converge. Right?
Right. -1.
This says prove or disprove that if a to the n squared converges, that doesn't necessarily mean a sub n converges. So just because a n squared converges does not mean that a n converges. So give us an example of that.
When an is -1, because an to the n.
What do you mean? Why are you talking about a n to the n?
Because that's how we did it. We did it an to the n.
No, we did an minus
an is just representing some sequence. You don't do an operation on sequence.
Right. So it's -1 to n.
equals, there you go.
Okay.
-1 to the n. If you use proper notation, then you would probably make sense of it.
I wasn't thinking of that as a series.
Yeah, sequence, not series.
Of course.
Parentheses, or these graphics. Right? That's an algebraic expression. Ah, now it's a sequence. And now I know exactly what you're talking about. Now it makes sense.
And
Okay, so now question, does this converge?
No, it doesn't.
How do you know?
Because -1 squared is 1, and then -1 cubed is -1. So
I said
Right, the sequences of, or the terms in the sequence are -1, -1, -1, -1, -1. We call that an alternating sequence. It doesn't converge. And it'd be real easy to prove that it doesn't converge. Prove it real quick. 1. Assume, by way of contradiction, we're going to do this by contradiction, the limit of, we'll just plug in the extra sequence here, -1 to the n is equal to some number a, right? In other words, assume by way of contradiction that the limit exists. Okay? Now we have two cases. Either n is positive or n is negative. Well, maybe we'll take an epsilon real quick. So how do you disprove something?
you proved that it's common.
You find an epsilon and you show that at no index can you start and go from that index onwards and have it within epsilon of whatever it converges to. So when you're proving it converges, you're given an epsilon and you find an index. When you're disproving it, you pick an epsilon and you show that there isn't an index. Does that logic make sense?
Yeah.
How you disprove? Now you weren't required to disprove on this one, but it's a common problem that you should know how to do. So assume by way of contradiction that this thing exists. So now I need to find an epsilon. I need to pick an epsilon that I know will work. Well, you already know in your head what? That this thing alternates between -1 and 1, right?
Yeah.
So what epsilon do I need to pick to make sure that it doesn't capture both these points?
You think about 1, or you think about -1?
Yeah, anything actually lower than 2,
2, yeah.
right?
Right.
Because I can't get my whole sequence with an epsilon.
Right.
I need to find an epsilon small enough
So there's
that I know no matter where you start the sequence, you'll get a term outside that epsilon.
Make epsilon 1.
Yeah, so epsilon equal to 1 is a pretty good number. We could have used 2, we could have used a half, we could have used 1/1,000,000,000th. There's an infinite number of epsilons we could have used. We just need to pick an epsilon. So, 2. Well, let epsilon equal 1, comma, and observe that epsilon is greater than 0, maybe. So that you know it satisfies our definition, in case it wasn't obvious. So now epsilon's 1, right? So if we're saying it converges to this point, if the A that we're claiming this converges to is this point over here, then epsilon gives us that interval, right? And if we're saying it's over here, then epsilon gives us that interval. And either way, neither of those intervals contain 2 points that we know will eventually get in a sequence no matter where we start. Does that make sense?
Yeah.
Okay. 3. So since I know this thing converges to A, and since epsilon's positive, then I know that there must be some index, such that from that index onwards, this sequence is within epsilon of A. Right? Using the definition of convergence real quick. Now, remember that we're doing a proof by way of contradiction. This n doesn't actually exist. Right? So, impossible picture that we're setting up here. Then there exists big N in the natural numbers such that a sub n minus a is less than epsilon for all n greater than or equal to big N. Now you should kind of be able to piece it together from here yourself. There's 2 cases. This big N is either even or odd. Right? If it's even, then what's this term?
It's 1.
It's 1. And then n plus 1, which is bigger than this n, is odd.
Right.
Which again gives a negative 1, which isn't in there. And then if this is odd, then when you plus 1, you get an even. So those are the 2 cases that you need to handle. So maybe observe that n is either even or odd. Now I'll just show one of the cases, no reason to show both, but you know how to do the other one if I did one, right? So which case do you want me to do? If big N is even, then A sub big N is equal to 1. And A sub big N plus 1 is equal to negative 1. Right?
Yeah. We're already outside of our limit.
Right. So we already know that this has to be within 1 of A, and this has to be within 1 of A.
And they're 2 apart.
And they're 2 apart, so they can't both be within 1 of A. Right?
Right.
That's all you say. We're done.
Okay, so real quick right here. Shouldn't this be big N?
Now, we found an index such that this is true for all little n from big N onwards. Right? This is true for big N plus 1, for big N plus 2, for big N plus 3, onwards. That's why we can do these 2. Both these 2 satisfy this condition.
So this term is saying we can find an n, and it's correlated to this n, obviously, right?
This n is always greater than or equal to the n we found.
Okay.
Remember, this is an index in the sequence where this is true from that index onward. Right? Maybe index 57. So we're saying from index 57 onwards, this is always true. Did I lose you in all that? Do I need to carry out how you should all the contradiction from this last part?
That's the
Wait.
definition of limit right there. If it converges, that has to be true.
The definition of a sequence converges, or the limit of a sequence exists, same thing. The definition of that is that.
There's this.
It's hard to just say it, you need to see it. We're saying the limit of an equal to A if and only if for all epsilon greater than 0, there exists big N in natural numbers such that an minus A is less than epsilon for all N from that index onwards.
That's it.
That's it.
Hey,
That's the definition of convergence.
can you explain to me the absolute value of an minus a?
This
Sure.
is the distance.
Oh, okay.
And remember,
the distance.
the distance between some term in our sequence and the number it supposedly converges to is less than any positive number you can think of from some index onwards.
It honestly makes sense. Like the logic, like I see exactly why they're saying that.
Yeah, it should make sense. Okay, so that's how you would have done a little proof by or prove that this is false.
So you're saying an is any term in your sequence?
If there's a
The
sequence.
same way, look, this notation is very similar to this notation.
Yes.
It's very, very similar.
Yeah.
Right? So AN represents the nth term in this sequence. A1 is the first term. A2 is the second term. A3 is the third term.
Mm-hmm.
Just like here, f of x represents what x goes to. A sub n represents what n goes to. And n is just the natural numbers. It's 1, 2, 3, 4, 5, 6, 7, 8, where x is any real number.
So
Typically
basically
with
you
sequence.
can. So an is not necessarily the sequence. It's.
It is a sequence, the same way that this is a function.
It's the domain.
Oh.
Yeah.
Oh, sorry. A sub n, we think about this as the range of the function. Same way that f of x represents the range of the function. X is the domain, f of x is what comes out. N is the domain, a sub n is what comes out. Right? You've also seen this as y, just the y values. Same thing.
I actually think this is my biggest holdup. Is trying to think of these things as sequences, not anything else. Like in my proofs, like, well, I showed it to begin with was my biggest problem.
Well, I don't know how else to say it except for it's a function whose domain is the natural numbers.
Right.
I mean,
What doesn't converge?
That doesn't
This.
converge.
Okay. Why?
Because it's
I'm
alternating.
saying because. Yeah, it's alternating. Oh.
Yeah, but like 6x.
Your range, right? So you're saying the sequence is the range,
okay.
and what's in it is the domain? Okay.
Remember when you drew the two graphs? The
Look.
difference between a sequence and a function?
First off, what's a function? Down brass tacks, what's a function? Lowest level.
It's when you put it
It's a set of ordered pairs such that every left-hand value goes to a unique right-hand value. That's what a function is. Here is a function. There's a function. A sequence, a sub n, is a function whose domain, or all the left-hand values, is all natural numbers. So I can't write it out because there's infinitely many terms. But if I start writing out this sequence, I would say, all right, 1 goes to -1. 2 goes to 1. 3 goes to -1. 4 goes to 1. And I can keep writing it out that way. There's infinitely many terms. Now, because we're kind of lazy, we already know that 1 went to the first thing, 2 goes to the second thing, 3 goes to the third thing, 4 goes to the fourth thing. So now we use notation that's not proper, but we use it because we're lazy. And we just say, to write this sequence, I'll just rewrite it this way. -1, -1, -1, 1. I just write out the range. Because I already knew what the left-hand thing was. The left-hand thing of this was 1. The left-hand thing of this was 2. The left-hand thing of this was 3. The left-hand thing of this was 4. Right? So sometimes we just write it out this way. then our really, really shorthand is, for any n, how do you get the right-hand thing? It's that. There's our really, really shorthand way of writing it.
Okay.
The same way, let's do the exact counterpart for this function, f of x equals x squared. What is that function? Let's write out some things in there. Once again, there's infinitely many things in there, and I can't write all of them.
1 to 1.
I can do 1/3, 1/9, right?
Mm-hmm.
I can do 0.25, 1/8, right? -749. There's infinitely many things in there. I can't write them all.
Okay.
But as a shorthand for capturing all this, we write. It's a shorthand for writing out this infinite function.
Okay.
The same way that this, and we might write it this way, is a shorthand for writing out this infinite function. But this is a special function. This is one whose domain is in actual numbers. If nothing, this isn't necessarily special. It's all real numbers.
Okay, but in convergence, you're having your an, so your whole sequence minus your limit, because a is your limit.
Right. Hold on.
It's a term.
You don't use, how can I say this right? If A exists, then it converges. The limit of a sequence existing and a sequence converging are the same thing.
Okay, so will you show me diverging?
This is a diverging sequence.
Okay,
Here's another diverging sequence.
6x. That's it.
There's another diverging sequence. What does 1 go to?
1.
1,
What does 2 go to?
2,
What does 3 go to?
3,
What number are we getting closer and closer to?
infinity.
We're not getting closer and closer to the number. Infinity is not a real number. It's part of what we call the extended reals, but that doesn't matter. So this doesn't get closer and closer to a real number.
So you're saying if the limit,
So it diverges.
if the limit approaches infinity,
No. If the limit does not approach a real number, then it diverges. Maybe it approaches infinity. Maybe it approaches negative infinity. Maybe it alternates between 1 and -1. Maybe it jumps all over the place. Maybe it's like a random number generator. It just gives us a random number every time. It doesn't approach a single number, get closer and closer to a single number. So if it gets closer and closer to a single number, then it converges. Then it has a limit. If it doesn't do that, then it doesn't converge. It doesn't have a
question, Donnie. It's one of our problems. Does this sequence converge?
Equals.
You see my pattern?
Yeah, you're writing out all the rationals.
Obviously it doesn't.
Now,
Doesn't?
no, because it
Jumping
goes
all
to
over
1
the place.
several times.
Yeah, it goes
Well, I
back and
just
forth.
see, how I think of it is it goes 1, 1, 1, so it feels like it's going to 1.
right, but think about this sequence. 1, 1, 1, 1, 1, 1. So it's going back to 1.
But James's point is,
But in your sequence, I'll also get an infinite number of 1/2.
Okay, I didn't understand that. What do you mean also?
Well, look at it.
1/2.
So you wrote 1 over 1, right?
Yep.
Then you wrote 1 over 2, 2 over 2. Then you wrote 1 over 3, 2 over 3, 3 over 3. Then you wrote 1 over 4,
And
2 over 4, 3 over 4,
James, what
4 over 4.
It is 4B, or, sorry, 4D or 4C, something like that.
So look at
Problem 4, because we're dealing with this sequence.
You're going to get 1 over and over again, an infinite number of times.
And
You're going to get 1/2 over and over again, an infinite number of times.
Okay.
I'm also going to get 1/3 an infinite number of times. Here's 1/3. I'm eventually going to get 3/9,
Yeah.
and etc. I'm eventually going to get 9/27. I'm eventually going to get all the infinitely many ways that we could write 1/3. Yes, I should have put
It says show that an equals 1/2.
Yeah, and this is where it equals 1/2.
Show where it
Is
is.
this where you have k
A
over
and
j
the
plus
sequence
1?
Yeah,
and
it's that
this
one that
sequence.
he messaged me in the group chat. So you'll eventually get a 1. You'll eventually get a 1/2. And I think it asks you to find when you'll always get like a 1/2 or something like that.
It says show that a equals 1/2.
Okay, well, we'll get to the problem when we get to it. Let's continue with what Jacob was doing. So Jacob was saying that this was false. In other words, just because a sequence squared converges does not mean that the sequence itself converges.
Yeah.
Just because a sequence squared gets really, really, really close to just one number doesn't necessarily mean, just because the square of a sequence gets really close to one number doesn't mean the sequence itself gets close to one number.
Okay, so obviously, I should say obviously, but if you squared this, then if you multiply exponents, 2n will always be even, and for every even in this sequence, we're going to get 1, or it converges to 1.
Right. So if an equals this, does this converge?
No, because
No.
it's an alternate
No.
sequence.
But if we do,
But if you square it, then yes.
an squared, well, what's that equal to? Right?
It'd be 1, yeah.
Square it, which, okay, you can already see it's just 1 over and over again. Right? So this converges, because it's just 1 over and over again, so it converges to 1. This doesn't converge. It alternates
Right.
between 1 and -1. Alright, so there's an example of a sequence whose square converges, but the sequence itself didn't converge.
How come this whiteboard is so trash like that?
They keep washing it with stuff instead of just erasing it. Because it makes it all nice, but it ruins the whiteboard. It makes it look nice. They care more about looks than functionality.
It's an end room shop.
I know. I've already gone after it for it.
We'll go away.
No, I think it's only going to get worse. The whiteboard can't improve. It's not like you.
This board is better than it was last
No, it's not.
year. And it was erasing better at the start of the year than it was at the end of the year last year.
Maybe there's some stuff that you can clean up with that helps, but whatever she's doing isn't helping.
Probably Xbox.
Okay, what's the next part?
I actually have a question for the next part.
Well, that's what Jacob's going to explain to you.
If this sequence an plus bn converges, then the sequence an and bn also converges. Let's do that.
So is it true that if the sum of two sequences converges, then each of those individual sequences converge?
Yeah.
And it's false.
Isn't that one of your...
Now, we prove that if the sum of a sequence converges, the limit of the sum of the sequences is equal to the sum of the limit of the sequences is what we proved. That's the best way to say it. So he needs to find two sequences, AN and BN, whose sum converge, but individually neither of them converge.
Can they both be the same sequence?
Sure. If that ends up working, but that's not going to work.
-1 to the n plus -1 to the n.
It's -2 to the end.
Oh, I see.
Oh, sorry. I was picturing what you were saying wrong. -1 to the n plus -1 to the n is 2 times -1 to the n. Is that what I said before?
No, you said 2 to the n.
So we already know that if you take a sequence and you multiply a convergent sequence and you multiply it by a constant, it still converges. So if you add a sequence to itself, that's the same as multiplying it by 2. And if the sequence converges, multiplying it by 2 still converges. You can multiply it by 10 trillion and it still converges. You can multiply it by anything and it still converges. That's something that we proved.
Yeah.
So let's see what he's saying since he's not talking.
False.
He's saying false. If we have a n equal negative 1 to the n plus 1 and b n equal negative 1 to the n, then
And
this doesn't converge, this doesn't converge, but their sum together converges.
Yeah.
Now that's kind of a convoluted example.
Well, that's the exact one you showed.
Well, I just added on to what you already had. You have done an equals n and bn equals negative n. There's a nice simple example as well.
This is easy.
But yeah, perfectly valid, works. Doesn't converge when you add them together, 1, negative 1, 0. Negative 1, 1, 0. 1, negative 1, 0. It converges to 0. So, the sum of two sequences converges, but individually those sequences don't converge. There's one example, here's another example. That doesn't converge, it goes off to infinity. That doesn't converge, it goes off to negative infinity. Their sum converges to 0.
Right.
Make sense? So there's two examples showing that that's false.
So this one we have to prove.
Awesome!
We have to
I'll
prove it on
find
the
out
workbook.
what you.
Why don't I have oh yeah, we already went over that. This is when the page turns, so I didn't do this one. Oh, but then I did do it. I should write my notes up.
How do you spell does? D-O-E-S? I keep switching my S and my E.
Okay. In the sequence a plus an plus bn and an converges, then the sequence bn also converges.
Okay, so if you have two sequences, an and bn, and if you know that an plus bn converges, and you know that an converges, then an plus b, or then bn converges. That's what he's going to prove.
Who the heck is
That
it?
was-
System in.
I want you to try erasing what Jacob writes on the whiteboard and see how crappy it is.
Where's mine? Okay.
Erase what I have at the top there, not what he wrote.
No, leave that.
Oh, never mind. Write something. You see how obnoxious that is?
Why is it like that?
Because you keep wiping it with water,
Yeah, because
and you need to quit it.
Pauline says not to use the whiteboard.
Well, just
Well, I'd
erase it.
rather you just erase it and have it ugly than put water on it and ruin it more.
Like you're not the only teacher that uses this room.
I'm pretty sure every teacher agrees that not being able to erase a whiteboard is a problem.
Okay, we'll clean it with whiteboard cleaner today.
No.
Clean it with whiteboard cleaner or just erase it. One of those two. Just don't use water.
Okay, all, got it. I use whiteboard cleaner.
That was lucky.
You caught
She came
it.
by.
Yeah.
Do I need to do this?
Well, only if you're talking about sequences. Okay. I mean, what you're doing is fine, but it's kind of making weird sense. If the limit of an plus bn and an converges,
I didn't mean to do that. I should have said it exists, right?
and the limit of an exists, right? There you go. Now it's starting to make sense with what you're saying.
And I give this time with these things to do.
But we're not proving if the limit of those.
You're supposed to do one of two things. Either show that the statement's false, or if it's true, prove it. So there's an A, B, C, and D. We said A is false, here's an example. B is false, here's an example. C is true, here's the proof. See how that works?
Yeah, I didn't prove it because we did it during.
No, my question
Well, that
is.
just means you need kicked.
I do need kids.
Alright, well, I'll catch you later.
Oh shoot.
Trying to get you when you least expect it. Probably gonna wait till you're down. Yeah, that's a good strategy.
Are you saying if?
Kick them while they're down.
Oh.
Aren't we asking if an plus bn converges, and an converges, then bn converges, right?
Right. The limit existing and them converging is the same thing.
Oh.
Remember that. So, it's not since. It's let the limit of this equal this, and the limit of this equal this. We don't know they equal that, you're saying let them equal that. Whatever the limit is, let's call the limit of whatever this thing is a plus b. That's fine. Any number can be represented as a sum of two numbers.
Okay, I'm confused with what he's proving. If the limit of that and the limit of that exist, and the limit of that exists.
Right, so another way to say it is, if the limit of an plus bn equals a plus b, and the limit of an equals a, prove that the limit of bn equals b. That's another way you can think about this, right? He's saying, if the limit of this thing exists, and we call it a plus b, and the limit of this thing exists, and we call it a, then the limit of this thing exists, and we're going to find out it's also b. The b that we put here, whatever number it is, that you have to add to the limit of this thing to get the limit of this thing. Whatever that b is.
So it's saying that both of them have to have limits, or if one of
If
them.
this has a limit, or this converges, if this limit exists, or this sequence converges, and this limit exists, or this sequence converges, then this limit exists, or this sequence converges.
Has to exist?
Yeah.
Okay.
What do you mean has to? If we're saying it exists, then we mean, how else do you interpret exists? Sometimes exists,
Yeah.
depends.
Depends.
Maybe if you pick the right one,
Mhm.
but if you pick the wrong one, then it might not.
Yep.
Then you don't prove it's true, you prove it's not true with counterexample,
Okay.
right? If I just say the sum of any two numbers is 2, when I say look at 1 plus 1, see a problem with that?
And plus.
Explain to us what you're doing, Jacob.
Okay, so if these two exist, then we're going to use the definition of our limit, and we're going to throw an into right here, into these parentheses, so and we know our an is this, and so we're trying to get our proof of the limit onto,
So he's using the definition of this.
yeah,
We know that this converges. So that means for any epsilon you pick, there has to be an n1 such that this definition holds. And we know that this converges.
so you have
Which means for any epsilon, there has to be an n2 where this definition holds.
Okay.
That's what he's doing.
So, an plus bn minus a plus b, because that's our a plus b is our a, and our an plus b is
Absolute value, no, not brackets.
Yeah.
wow, sorry.
No, not that.
Maybe it's just squiggly.
That was terrible.
This?
Yeah, look at the definition.
Right.
Such that the absolute value of that
It's less than epsilon.
is less than epsilon
And
for
what's
all n greater
No,
than
you say
n1.
after. Okay, never mind. Epsilon over 2. You'll figure out why later. This just needs to be a positive real number. So you can say epsilon over 2. For all. Is that for all?
Yeah, but put it right here. Because then you're going to have the other equation. So we can group it together and have that easily.
All values. For all little n greater than n.
Okay? Greater than or equal to. Just look at your definition again.
For
What
all
does
n
greater
less
than
than.
mean?
Hey, there are 2 n's. Greater than or equal. Yeah, there we go.
So which n? I don't know what big n is. All I know is an n1 and an n2.
To the max. Right?
Here's the problem
No,
with getting
you-
so far away from that.
N1, I meant to say that. I see what you're
It's
saying.
not logic.
N1, we're dealing with this, and
Okay.
then N2, we're dealing with this one.
Wait,
Yeah.
can't you just say let n? Can't you say that? Just say for all n greater than n, and then let n be the max of n1 and n2.
So you can. Don't get carried away trying to do the whole proof in one line. Write down concise thoughts.
Yeah, but I'm
So
saying.
he's just going to write down exactly what this definition gives him for this, and what this definition gives him for this. And then he'll go through the logic that you're talking about.
Oh.
Oh, I don't need to say that again.
Yeah, you already said that.
And a n, that's going a n minus a is less than epsilon over 2 for every n greater than n2. And then 3 or
Look at your definition again. There you go.
2 left and equal max and 1 and 2. Okay. Now let's move into algebra from here.
Is everyone up to date with him so far?
No.
Yeah.
Alright, let's get up to date.
Well, we needed to do sine math to get our epsilon over 2.
Right, so you might wonder where the epsilon halves comes from. Is that the only thing you're wondering about?
Yeah.
Okay.
For all epsilon greater than 2, there exists.
Epsilon
okay.
just has to be.
Right, so pick some epsilon greater than 0. Right? Then there has to be an index for this sequence and an index for this sequence such that this is true from that index onwards when it's less than some positive number. He just said epsilon halves here.
Okay.
And this is true from that index onwards. And he did epsilon halves here as just positive number. Now you might be confused why he chose epsilon halves here and here, and we'll see that later in the math. This came from his scratch work that he did on the side.
That's right.
But do you see how his definitions give him this and it gives him this? Do you see how that just falls from the logic that we already know that this thing converges and this thing converges? Okay, so if you're good on that, then I think we're good to go forward.
Okay, so on this step, then we're gonna say bn minus b, but it's not necessarily the limit of bn.
Well, remember where he's trying to get. He's trying to get ultimately that the limit of bn is equal to b.
And to get that, you need to say bn minus b is less than epsilon.
Right, so he needs to get bn minus b is less than epsilon for all n greater than or equal to some index. So he needs to get this. He gets to use the fact that this is less than any positive number he can think of from some index onwards, and that this is less than any positive number he can think of from some index onwards. So those are the two pieces of information he gets to try and prove this.
So
So he's got to introduce this term into there somewhere, and he's going to introduce it now.
see if I can do this right, because I might not be able to. bn minus b, and then we're gonna add zeros just to get our other terms in. So plus an minus an plus a minus a.
You see all that? That's a lot of crazy thought right there. Why on earth is he just adding all that crap and taking it away?
And it's so I can group it. So this equals.
And hey, go back one line, Jacob, and write bn minus b equals all that. No, just erase the 3. Just add to the left-hand side. You see what I mean? Help them see. No, bn minus b equals that. Absolute value.
All right.
Says it's good to make this term actually show up. That way they can see what you're doing. So he's got to show that this is less than epsilon, right?
Mm-hmm.
So you've got to introduce this term somewhere. So he introduces the term,
That actually helped.
and now he rewrites the term, but he's just adding in these other terms that showed up here, things that he knows about. He knows about these ANs and these A's, So without changing the value of this, he introduced the terms. Right? So now we have an a in there a couple times and an a in there a couple times that he can work with.
So,
What? No.
I'm wondering how we got.
Yeah, I'm wondering how
What's this
we
equal
got
to?
0.
What's this equal to?
Oh,
But
okay.
how did he get a negative b?
Holy cow.
that's this.
We started with this.
Where did he get that?
Plus 0.
We just know, ultimately we need to show this is less than epsilon.
Oh, okay.
That's what we're trying to get.
So we're taking it, adding a bunch of information we do know, showing that it's less than that.
Right. So, two things to keep in mind. A, we're trying to show that this is less than epsilon. That's where we're trying to get. The information we get to use, this is less than any positive number from some index onwards, and this is less than any positive number from some index onwards. So that's the two pieces of information we get to try and prove that this is less than any positive number.
Okay.
So he wants to use that information. So we started with this, and he introduced terms that will probably let us use this information up here. We'll see. But it's a common strategy to add zeros to introduce the terms you want to talk about.
So, what I'm thinking is, and I could be wrong, I'm not looking at my notebook. This, you have bn, positive bn, and you have positive an, and we could get that. But you also have negative a, and you also have negative b, so you can get that. So that's what I'm going to try to do.
Perfect.
So, we can agree that you can rewrite bn and an to the an first.
Right, commutative property.
Bn, and then parentheses. And then we have negative a, negative b, so we're going to write it out like negative a plus b. Okay, and then we have, and then our other two terms remaining are negative an and a.
Yes.
So,
Negative a and then positive a.
so plus negative an plus a.
Okay, you go with the algebra up to there. He's
How
just
do you get
reordered terms.
Oh, never mind.
Do you see where all the terms went?
Yeah.
Yeah.
Okay.
Okay, this is where I'm going to struggle trying to isolate this.
Well, don't you first need to get your, first
Well-
off, your an not negative and your a negative?
Right.
So how can you do that?
Is he gonna show where epsilon is
Can you
over 2?
divide? No.
Yeah, you'll see where the epsilon over 2 comes from. Can you divide what?
I was thinking, can you divide over -1, but then you'll have to.
If you multiply over -1.
Okay. How does our absolute values work in this situation?
Well, okay. So two things that you might be keeping in mind with the algebra here. One thing is what Jeanette is saying. We have negative an plus a, not an minus a.
Right.
And then the other thing that you should be keeping in the back of your head is the triangle inequality. Triangle inequality says that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Anytime you need to split up an absolute value, you want to use the triangle inequality. So you see that you kind of have this right here, and you kind of have this right here. So ultimately you want to do that split up.
So this is a, this is b.
If you want to use the triangle inequality and do that, you can.
Which you won't want to do.
How do you know that that's b?
That's one term. Right?
He's just saying if you use the triangle inequality, it doesn't matter how you group it, right? I'll show you another example if I could use the triangle inequality. If I have a plus b plus c plus d, I can do it however I want. I can say this is less than or equal to and do these three grouped together and this one by itself, or these two grouped together, these two grouped together, or those three and that.
Okay.
So he's just arbitrarily going to group these together and this one, these two together. And the reason that he's grouping it that way is because he's seeing that this looks a lot like that, and that this kind of looks like that. So maybe that will help.
So this is less than or equal to and plus
So there's a negative AN in front of that, in case you can't see it.
Yeah. So,
That's a negative sign.
what does the absolute value mean? Doesn't the absolute value mean negative?
Oh, no, isn't the absolute, can't you say, the definition of a negative absolute value is,
Oh, can
can't
we
you
use
use
the
the
triangle
definition?
equality again?
can
On
you
this.
use the
If you
definition
want.
of absolute value to switch those? Can you use the definition of absolute value to make those
We're just
positive
doing
or
one.
negative?
Can you?
Yeah, I'm gonna say yeah, but then you would have to take
Okay.
it out of absolute value.
Let's
wouldn't you?
think about what it means to
But then can't you put it back in?
the absolute value of A.
Alright. Something we proved with absolute value in the past already. The absolute value of A minus B is equal to the absolute value of B minus A.
Okay, so
How does that help?
work A minus
Oh.
AN. Okay, AN is I guess you say A minus a positive AN.
How do I help you guys see this? You're so. You know what? I'm not going to give you any hints. That's enough. You should be able to figure it out.
We should be able to figure it out. Or we have to use a rule.
You're going to have to use what I just wrote there.
I just did.
Okay. If you think you did, then that makes me a little sad.
A is that.
How do you use that rule?
You reordered all.
Oh, okay.
Good duty.
Right? Because.
A and minus A. Now you did two steps in one. So now
okay,
walk
I
through
can
using
do
the
this.
rule.
I can do this. This is exactly equivalent to A minus AN,
Wonderful.
which is exactly equivalent. Or,
Using that rule gives us that when you have the absolute value.
which makes sense, obviously, because 7 minus 3 is 4, and then 3 minus 7 is 4.
It's negative 4.
Well, I'm saying that's the value.
Oh, well, you didn't say that, so you weren't saying that.
That's what he did though, right?
Yeah, he used the fact that the absolute value of A minus B is equal to the absolute value of B minus A. How do we know that? Because the absolute value of A minus B is the distance between those two numbers.
Right.
And the absolute value of B minus A is the distance between those two numbers. And the distance between those two numbers is the distance between those two numbers. And so you can think about it as the distance from B to A, or the distance from A to B, and it's logically equivalent.
All that equals. You know what? Let's just say this one. Can we just change this?
No! You could have made that leap in your head when you were writing it, so you don't get it now.
Oh, that's why we use our extra corner first.
And use F sharps on your proofs for when you've done messed up, and you went down a path that doesn't work. And so you don't give me all these scribbles everywhere.
We can say that's equal. Like we don't have to say less than or greater than, right? Or less than or equal to.
Depends on if you're doing something that's equal or not.
It is.
For this substitution, it happens to be equal, yeah. Everyone good with where he's written up to so far?
Yeah.
Okay, so now we have. This is the exact limit of. Or this is the exact definition of the limit that.
No, it's not. That's just the absolute values of terms. The other one's just the absolute value of the subsequent terms.
Okay, so now we need to say, well,
No, now
we
you say
use our
that
ends.
No.
Ah, there you go. You need to introduce your ends into this somehow. Your epsilon halves. How do you do that?
Did you say that that crap is all equal to, or
Okay, notice that.
you say that it's less than equal to epsilon of 2 plus epsilon of 2 over 2.
Well, we know, okay. So what
Which
we
is
know.
less than epsilon.
This is less than epsilon over 2 for every n.
Oh, I kind of.
This is less than epsilon over 2.
It's kind of like what you're
And this is
telling me
less than epsilon over 2.
Jacob,
when I was adding those two indexes together.
you have all of this
2
crap,
over
right?
the square root
Which
of
is
big
less
N
than epsilon,
plus
so you
1
can
over
say
the square
all of
or
this
plus
crap
1 over
is
big N
Epsilon
is equal to 2 epsilon.
is
right?
epsilon over 2
Plus
Plus-
epsilon over 2.
epsilon over
Yes.
2
Oh,
every
which
value.
is less
Wait,
than,
for every value.
just watch it, which is less than epsilon, which means that all of that crap is less than epsilon.
Look,
For every
when is it less than epsilon?
For all of your n's, when, for every n greater than n big N, but your n is your max.
There you go. So make sure you understand the logic of this. We know that this absolute value is less than epsilon halves for all n greater than big N1. And we know that this absolute value is less than epsilon halves for all n greater than big N2. Which means if we let big N be the max of N1 and N2, then this is true from big N onwards, and this is true from big N onwards. You follow the logic there?
Yeah.
If this is true from 7 onwards and this is true from 14 onwards, both of these are true from 14 onwards.
Yeah.
Right? The maximum are both. So a bunch of algebraic manipulation. You start with Bn minus B, you add 0, you regroup terms, use a triangle inequality, use, it doesn't have a special name that I know of, and then we know that that's less than epsilon halves and that's less than epsilon halves for n from big N onwards.
That's actually cool. Think about what we just did. We just proved that if an, the limit of an does exist, and the limit of both of them exist, then bn exists.
Yeah, not only does it
Period.
exist,
No matter what happens, we know
but it
that.
equals that b.
So now we know that every single time when you come across any sets of sequences that converge and one converges, the other one has to converge.
If you come across two sequences whose sum converge, and you know that one of them converges, then the other one converges. Yes, you know that.
Has to.
That's awful.
Has to. And now you can use that information, the same way that we know our different rules for convergence. So now let's talk a little bit about this epsilon halves that he just introduced out of nowhere. Where did that, how did he know that that was a magic epsilon to use there?
Because I knew
it has to all
we
be
have
less
to have
than
that.
epsilon.
So when he was getting ready to come up with the answers to this problem, he started out with, and by he I mean me because he wants me to solve this. So here's what I did. I started out with, I need this less than epsilon. That's ultimately what I knew I needed, right? And I knew that I need to use that this is less than a positive number, not necessarily epsilon halves. And I knew that this was less than a positive number, not necessarily epsilon halves. So I knew I needed to use that information. So what I started with is I started with this thing, Bn minus B, right? And I kind of just started with this line that he has right here. So I said Bs minus B, what does that equal? I knew I needed an AN and A in there somehow. So I did Bn minus B, add an AN minus an AN, plus an A minus an A, same thing he did there. And then I regrouped my terms to make it show up how I wanted it to over there. So we had AN plus BN minus A plus B minus, I wrote it this way, A minus AN, or AN minus A.
You can't do that.
Yeah, you can.
You just made a leap in your life.
Negative AN plus A. Exactly what you had.
Oh, right.
Negative AN plus A.
Right.
So here's what I had. Then I use triangle inequality, which gives me that this is less than or equal to AN plus BN minus A plus B plus absolute value of AN minus A. Okay.
Wait a minute.
So then I do.
Look, for our triangle inequality, we have to have the terms adding each other. None of your terms are adding each other.
Adding and subtracting. How can I say this? The definition of subtraction is adding a negative number. So yeah, it's kind of using two thought processes in one, but I'm not going to dock you for doing this.
Okay.
Okay? Alright. Huh?
That doesn't make sense in my head.
It's the exact same
It's
math
the
as what
exact
you
same
got.
logic.
I understand that we got the same exact thing.
Well, look, you use the triangle inequality here when it's plus, And then you use the fact that that can be rewritten when you swap the terms.
I'll zoom out.
Another way that you can think about it, triangle inequality, the reason that this has its name is because when it first showed up, it showed up with triangles. And what it's basically saying is that the hypotenuse of the triangle is always shorter than this, not the hypotenuse necessarily, but if you pick two sides of a triangle, it's always longer than the third side. It's definitely true. Oh, sorry. Any side of the triangle is less than the sum of any other two sides.
Right.
Right? Am I still saying that right? Yes, the sum of any two sides is bigger than any side of the triangle. Oh, that's not going to be a good analogy like I thought. Never mind. Okay. So, forget about that. Anyways, triangle inequality, there she blows. And then I knew that I needed this to be less than epsilon. I needed a leap to make this less than epsilon. That's the leap I need to make. Now I knew that I could make this positive smaller than any positive number, and I knew I could make this smaller than any positive number. So what two positive numbers could I use here to make sure that this whole thing was less than epsilon?
Oh.
So you could have chosen make this one less than epsilon halves, and make this one less than epsilon halves. You didn't have to. That's just what I chose because that was easy to do, right?
Okay, now
I could have made this one less than 3 epsilon fourths, and this one less than epsilon fourths, and proved it that way as well.
Okay, could we have said epsilon over 1,000, epsilon over 1,000, and then that's obviously less than epsilon?
We could have picked massive numbers here as well. Or really small numbers here as well, yeah. So I could have picked something like, well, can you do that?
Because that's going to end up less than epsilon, and
Yeah, so yeah, we could have. So we could have also just did epsilon fourths, or epsilon 4,000. 40,000. And yeah, it still would have worked. But it's just convenient to use epsilon halves.
Yeah.
Add them together and you get epsilon halves. So this is where the epsilon halves came from. So I knew that a sub n plus b sub n converged, which means that I knew that I could get this less than any positive number from some index onwards. And I knew that a sub n converged, which means I knew that I could get this less than any positive number from some index onwards. So I could get both these less than any positive number from some index onwards, and the positive number I chose was epsilon halves, so when you add them together you get epsilon. That's how the epsilon comes into the picture. So when you're doing these proofs, it's very common that you have this scratch work off to the side to figure out how you're going to prove it, and then you go back in and you just kind of use it, and when you're using it, you're like, what the heck, where'd that epsilon halves come from? Came from your side work, your scratch work, to figure out how you're going to prove it.
Well, you don't even have to do that. You could go through this, come out with 2 epsilon, and then see where you need to bring the half in. And just adjust your proof.
right, you go in your rings.
You could just do epsilon, 2 epsilon. No, you need to let them pick the epsilon.
It's not going to work, right? But
You can go
but
through
you
your
come to
rings.
the end and see, oh, I have 2 epsilon where I need epsilon. Maybe I should work with epsilon halves instead.
Yeah, or you could show it's less than, pick something that's not epsilon, c, some number c,
Right.
and then you go back and you say, give an epsilon, let c equal epsilon halves, or whatever.
Right.
But this is the common way you do it.
Just off to the side.
And you just arbitrarily introduce in these numbers, and you're like, where did those numbers come from? And you see later in the proof where those numbers came from. And so when you read the textbook, the authors can do that same
How
thing.
many have been doing that a lot?
This? For now.
I'm saying like
I mean, when
changing
we
the
have
epsilon
these-
values.
No, when we establish these limit properties, we're done calculating limits by hand every time.
Yeah.
I mean, you only calculate limits by hand to get comfortable with this definition over and over again. Make sure you thoroughly understand it. And then we start using our limit properties from there on out. Like, for example, the one that we ended on last time, talking about polynomials, which is ultimately going to lead us to, if I want to talk about, so I'll say f of x is equal to x squared, and I want to talk about the limit as x approaches 2, you're not going to prove that this is of f of x is equal to f of 2. You're not going to prove that every time you need to use that fact as you come along, because we proved that polynomial proof. And we handled it. And now this is just a special case of that. And you can start using this knowledge from there on out.
This is when we gotta start plugging in numbers without having to prove.
So you prove these things that you use later. That's the beauty of math. You prove and you develop these abstractions, these tools that you can use from there on out. So you only use this definition directly to begin with, until you get all the tools that you need. Right? And then you use your tools. Okay, so there's that one. Is that the end of problem number 1?
No, there's a thing.
What's D? D is another false? Lucky you. So the problem was the author asked 4 questions, and if it was true, you had to prove it, and if it was false, you had to give a counterexample. So C was true, so we had to prove it, and then D is false, so he's going to have to give us a counterexample. Would you hurry up? Wow. Make them watch this video when I put it up. Make her watch your work.
Does she clean this now?
Yeah, if you keep watching this whiteboard with water, making it worse and worse.
Just get whiteboard oil juice.
I don't know what it needs. I know what it doesn't need. That's cleaned with more water.
Hey, Min, did you wash my dry erase board?
Alright, if the sequence and the absolute value of an converges, then the sequence and also converges.
Not that. That's not reading around. Oh.
Okay,
So if the absolute value of the sequence converges, then the sequence converges.
Right.
False.
False?
Original sequence.
Wow. Someone's memorizing some information.
Yeah.
Or they're learning about sequences, one of the two. Hopefully the latter.
False.
If you don't put an exclamation point, I'm going to just, yeah. I like how if starts with a lowercase I.
It's an upside down exclamation point.
Oh, of course.
If that's value of A1 squared, then value of A n is always 1 converges. Then
Oh, right.
and
Alright, so if an equals -1 to the n, then absolute value of an equals 1 converges, and an doesn't converge. It's a little weird, but that makes sense. Everyone understand that? Woo! Alright, there was number 1. Who's doing number 2? Number 3 is harder, so
Jacob.
may as well jump in while it's easy. No, Jacob, you're now doing number 4. So we're going to set the pattern and then just continue from there. So, James or Janetta?
Take the bow, peeps.
Now I want number 3. You did not want number 2.
Why is number 3 harder?
I don't know. It's just usually how problems go. They get gradually harder. As a general rule.
I don't even understand what that means.
So 4 is really the hardest.
So you want to do number
Well,
2?
We're saying 4 is the hardest.
Sure. So you
Okay.
want to do it?
I know how to do it.
Come on, someone. Up. Here, boy. Here, boy. Here, boy.
I'm assuming it's me because I'm quick.
Oh, you stood up. I thought you were coming up. You're taking forever.
Oh.
Alright, get started. What we proven?
We are proving the limit of 1 over the square root of n is 0.
Alright.
Look, they're already giving us as n goes to infinity.
I think they did that the whole time.
Question. For all of this crap, it says, using only the Archimedean property, give a direct E epsilon.
That's just
Epsilon.
N.
It's basically saying use this definition directly using the Archimedean property.
Right.
Which is all we've done so far.
Is that
remember
not
this
the
one.
Archimedean
This is
property?
when I got pissed.
No.
No, and there exists an n less than, or,
The Archimedean property is there is no biggest number.
and there is, well, and there is a smallest number.
That's a result of the Archimedean property. So the Archimedean property directly is, for any number you pick, I can find a natural number bigger. The natural consequence of that is, for any small positive number you pick, I can find a smaller number. And that falls from this. You pick a really big number, call it C, right? And I'm saying I can always find a number n, so that n is greater than C. The corollary of that is, if you pick any really small number, epsilon, then I can find a number n bigger than 1 over epsilon. So you pick any teeny tiny number you want, I can find an n slot. This is true, right?
What?
Yeah, but.
Pick a teeny tiny number. This is a number. Any number you pick, I can find a number bigger. And it just turns out if epsilon is really tiny, then this is really massive.
Yeah.
So, pick a tiny number, I can still find a number n such that this is true. I can always find a number n that this is true. But then if you do some reordering, what do you get? You get 1 over n is less than epsilon.
Hey.
It's just a consequence of this. So we use this directly a lot, and we call it the Archimedean property, even though it's not really the Archimedean property. It's just such an easy corollary of it that we just.
So when we say Archimedean property, we can mean either there is a bigger number or there is a smaller number.
Yeah, but we kind of loosely use the Archimedean property that way, but what it really is this. It's just that this quickly follows from it.
Okay.
Alright, so we have proved that the limit of the series, 1 over the square root of n, is equal to 0.
Find the
Yeah, so start with some positive number epsilon. And we put our period at the end of the statement.
No, I thought you put it before. Then by the Archimedean property, there exists n in natural numbers such that well, what I want is that is greater than some epsilon.
So you want 1 over the square root of n is less than epsilon. That's not what the Archimedean property gives you.
Right.
So if you need to do some scratch work, do some scratch work on the side.
What it gives me is this.
Look, Jane.
Okay.
Remember how we did this? We said that 1 over the square root of n times 1 over the square root of n is 1 over n. So if we just say less than epsilon squared,
Well, don't say it like that. Here's what you say. I want this to be true. When is this true? And make sure you have 1 over n. What is 1 over n less than if that's true?
Epsilon squared, right?
Why is epsilon squared?
Square both sides.
Oh.
So by the Archimedean property, there exists n such that 1 over n is less than epsilon squared. That's true. Here's a positive number.
Then
For any positive number you pick, you can find a natural number such that 1 over natural number is less than a positive number.
okay.
That's Archimedean property.
Then
And then you use that to get where you want to go.
the square root of n is less than epsilon. Alright?
Right.
Wait, we can say that because,
Positive number, square root of both sides, still positive numbers, inequality still holds.
well, epsilon is just a positive number.
Epsilon's a positive number, yeah, and epsilon squared is obviously a positive number.
Now what am I trying to show? I'm trying to
Maybe
find...
go write the last line of your proof if you don't know where you're going. And work your way up a little bit.
Remember, we want to take it from, when you use the definition of a limit.
Just let me think about it.
Trying to show this is less than epsilon, right?
You're trying to show that the limit of 1 over the square root of n equals 0.
Mm-hmm.
When is that true?
And there's a number.
Write it down here. Write it out. The last line of your proof. Doesn't matter if this looks ugly. You're not writing this on a final piece of paper.
Therefore, box filled in.
Okay, aren't you trying to get the absolute value of an minus a is less than epsilon?
Yeah.
So what's your
did you
A?
say your an is 1 over square root of n?
Yeah, what is your A and your AN?
So now substitute.
Don't write A and AN.
I'm thinking.
Okay.
It's like easy. This would equal my 0, and this would equal my sequence, right?
There you go. For what? Look at your definition. There you go.
And greater than or equal to again.
Perfect. Now, not natural numbers. Some index n. Perfect. So you see that once you show this, you're done.
Mm-hmm.
So that's where you're ultimately trying to get it. And now you can work from the bottom up if you want. When is that true?
And that is true when the absolute value of is equal to which is less than absolute value of the index, which is less than epsilon.
Almost.
For all values in n. For
all n greater than or equal to big N.
Yeah.
Okay, write that. And let's see if that makes sense or if there's a problem there. Look at the line you just wrote.
Did he drop his absolute value too soon?
Well, no, the absolute value is fine. The absolute value of 1 over the square root of n minus 0 is just 1 over the square root of n. Definition of the square root function is it always gives a positive number. So that's always positive. The absolute value of a positive is just the thing itself. So that's fine. What's he missing?
You've got two cases. If your n is
If your n is bigger than n.
That's one case.
case number 2.
If your n is less than.
No, little n can't be less than big N.
Are you seeing this?
Yeah.
There you go.
Oh.
Ah, now we have a true statement on the board. Don't you love when we have those? There you go. And you're done.
Okay, where did you get your?
It's beautiful.
Is your index on line 2? Is that where you got your?
Yeah, by the Archimedean property, there has to be some natural number big N such that this is true. Right?
Okay.
And if this is true, then this is true.
Okay.
Right? And then 1 over the square root of n minus 0 is equal to that, right? That's just algebra.
Mm-hmm.
This is less than or equal to this for all n greater than or equal to big N. Why? The bigger we make the bottom, the smaller we make the number. So this is either less than or equal to this, right?
Which is less than.
Which we already know is less than epsilon.
Okay, James, now you have to do B.
Yeah.
So there's part A, proof A, now it needs to prove part B. And come next week, if you guys are not caught up on homework, in other words, I don't have all your 2.1 done and done correctly, you're out of the class. Don't waste the time with this. We need to make progress. And if you're not going to keep up with the material, you're not going to keep up with the class.
How
Get it done.
if we not kicked out?
You are going to write this down on a piece of paper, you're going to hand it in to me next week at the beginning of class, or you're not coming through that door.
So if we don't do that, there we go.
Yeah,
Then what
I was like-
happens? We have to go to a different class? Make up?
I don't know. I'll send you to Brother Ham if he can talk to you. Let's not worry about that case. Let's just make sure that case doesn't come up. Right? Easy peasy. You're going to have it all right there on the lecture.
Oh yeah, just right here.
I mean, all I'm trying to get you guys to do is understand the material. Like, I'm just trying to help you guys.
Yeah, we appreciate it. This has actually helped a lot.
Good.
Is that N plus S?
Bye. Why actually doing this?
But gonna be an epsilon greater than 0. Then I just want to note that 1 over big N can I see that?
It's true for really large values of n.
Yep. Okay. Then
I don't know if you're going to necessarily use that.
You can say it's less than names.
Well, one of those was less than the other. Which one's which?
The one with the 5 is.
and by the Archimedean property, there exists big N and natural numbers such that 1 over big N is less than epsilon.
Good. Not for anything. There just is a natural number where that's true. You're good.
Then absolute value of 1 over n plus 5 minus 0 is equal to absolute value of, or n plus 5,
Little one.
middle n plus 5.
Why did that get so white?
You gave it the magic touch. His skin's so white that just absorbed a lot of blackness. All right. Is what he wrote there true?
Less than or equal to. But
Okay, I-
that is
that's
such an
valid.
assumption that,
Hold on.
is that not an assumption?
Is line 3 true?
No, because he dropped the absolute value, would you not say?
No, he's
Would I
gonna
not
make
say?
it less than or equal to.
And could be negative.
Can it be less than or equal to?
Can n be negative if it's greater than or equal to big N?
No, because n's not.
All right, so that takes out that. Any other problems that you might have with
Yes,
that?
it needs to be less than or equal. Oh, no, not less than or equal to.
You're saying less than or equal to right here?
Oh, it needs to be, yeah, no, yeah, it's not ever equal to.
Oh, really? We're just gonna let line 3 slide?
Yeah.
It's not ever equal to.
You didn't put equal to.
I don't know, so we're good.
You think that that line's true?
Huh?
Okay.
Oh, wait.
No.
Wait. It's
Right
not
here.
true.
Oh wait, for all values of
It's not true. I know why it's not true. Because n plus 5 does not mean. Oh, yeah,
Yeah, it does.
That is true, guys.
If n is greater than or equal to big N, 1 over n plus 5 is always less than 1 over n.
yeah.
Because it's always, I mean, one thing I would have said if I were him, I would have put like a note that 1 over n is always, or plus 5, is always less than 1 over n.
That's what I was going to say to you.
But he encapsulated that thinking all in one go there. Right? So yeah, perfectly valid, perfectly good proof. That gets you full credit if that were on the test. But I won't put this one on the test. I gotta pick one that Jake will miss.
Yeah, problem 3. I told Jeanette, I said I know how to do these.
Okay. That was B, right?
Yeah.
Alright, next one.
Look at that.
Wonder who's gonna do this one.
It's getting whiter as we erase. Or maybe it's not.
Something about just using your hand to erase. Seems to be very
Yeah.
oil. Alright. Let's go, contestant number 3.
What we got?
Shrek.
So we're proving that the limit of 2 over the square root of n plus 1 over n plus 3 is equal to 3.
James,
Right.
we did this one in class.
We did not do these ones.
We did A.
I did this in class.
You did not do A in class.
Yeah, I did.
Because then how come I had to do it last night?
Wait, no, I'm talking about number 3.
Number 3A. We
You
did
did
not
it.
do
Oh, the 3 have an A and oh, it does have an A and B. They're just full of such small proofs.
Okay. Oh man.
Okay, so we're proving that the limit of this is equal to 3. That's what we're proving, right?
Yeah, okay.
No.
Yeah. We're going to prove.
Alright.
Okay, I'm thinking the first thing I need to do is make these 0.
No. Okay.
You gotta use
First thing you need is you need to grab an epsilon. Pick some positive number.
Let epsilon be greater than 0.
Okay.
And then you know from there you need to pick an index. And maybe you're stuck about how to go about picking that index. Right?
Yeah, but
What the heck? So let's skip down to the last line of the proof. Let's work up a little bit. See if we get any ideas I propose.
Okay, use the definition of the limit.
the definition of the limit is.
Yeah, what's the last line of that proof going to be?
A
Write
and
that out. Let me figure it out.
Okay, so it's gonna be 2.
Did you use limit? You did that crap out of your computer.
Black stuff on his desk. Scrapes
Minus 3, right?
Uh-huh.
For all
Is less than
epsilon.
less than.
There you go.
For all n greater than or equal to.
Some index that we need to find. Perfect. So that's our last line. Now, when will that last line be true? Play around with that.
Okay.
That is true when AN is less than epsilon. Right?
Well, that is true.
Well, no.
Well,
But you can simplify that. So here's your therefore. Right?
So the next line, we're going to take away our 3's.
Yeah, then simplify that thing. Start playing with it. Make it more workable.
Is there a symbol for therefore?
I think that there's some shorthand way to do it.
Is it 3
Like
dots?
3 dots in a triangle form.
is less than epsilon. Okay.
So you need that less than epsilon, right?
Okay, and then I'm thinking I need to get less
But
than
don't
epsilon
skip
and
straight
just
to
less than.
less than epsilon. What else could that be less than? or equal to maybe. Just keep playing with it algebraically until you get something nice and simple.
Right.
Therefore, false.
I would say that is less than 2n, which gets rid of my square, which is nice.
It's less than 2n?
Yeah.
It's less than.
Well, yeah, but 2n is massive. When you said 2n, what did you mean? Suspicious you mean.
When I'm saying 2n, I'm trying to get rid of this square.
Okay, just write out what you're trying to say.
Well,
Okay, that's almost true.
less than or.
Less than or equal, right? We need to handle the case where n is 1. If
Yeah.
n is 1, then the square root of n is the square root of n. But from 2 onwards, this is always bigger than this.
Jared, why don't you just take out your 2?
Well, let her keep working with it. Okay, so that's good. Now what?
Well, then you could simplify terms, which is equal to 3 over n.
Wonderful!
Okay, I have to prove.
So you need 3 over n, and the last thing, like, you're not really going to get this any simpler than this, right? I mean, I guess one more way you could have written it, get rid of the absolute value, 3 over n. And you need to find that that is less than epsilon for all n greater than or equal to some index n,
Yeah.
right?
Okay, so by the Archimedean property, there is an n. By the Archimedean property, there exists an n that is greater than or equal to big N, which is our index, right? Making that, would that not make that true by the Archimedean property?
Well, we didn't find this n yet. So look, ultimately what I need now is I need to find an n so that 3 over big N is less than epsilon. If I can find an n where this is true, then from that n onward, this is true, which gives us right?
Yeah.
So I need to find the n that makes this true.
Anything. It can be.
No. What does the Archimedean property say? The Archimedean property says for any number you have, I can find an n so that 1 over n is less than that. Anything you put in here, I can find an n that makes this true.
Yeah.
Okay? And I need whatever I put in here, I need it to give me this information.
Don't you need, well, don't you need epsilon over 3?
There you go! So over there, start working with your proof. Now you have the inside.
So then by the Archimedean property,
Uh-huh.
there exists, is it, would I say big N
A
or
natural number. Yeah, big N.
big N in the
Oh yeah, that makes sense.
natural numbers such that 1 over n
Is less than.
that is broken is less than epsilon over 3.
Perfect.
Let 3 be bigger than 0. Then by the Archimedean property, 1 over big N is less.
Okay, now you need
less
to
than epsilon.
manipulate your bottom one.
Well, what do
Well,
you have? So,
No.
So, you're on a good track.
Let 3 be bigger than 0.
My epsilons are all 3.
wait, don't I need to add for all n?
No.
No.
Not there.
Okay.
The Archimedean property says there is some, no matter how small of a number you pick, I can eventually find a natural number, call it big N, so that this is true.
Yeah.
Right? That's it. That's all the Archimedean property says. Okay. So I know there is a natural number big N that makes this statement true.
Yeah. So now,
Now don't you just put it back into
yeah,
its
now we
form?
know just if epsilon over 3, hold on, if epsilon over 3 is less than epsilon, which is true, which makes that less than this, which makes that equal, right?
Well, I don't know that this is less than epsilon over 3. I just know that this is less than epsilon.
Oh,
So you need to turn it into that,
so,
right?
oh, can't I just, shoot, what's it called? Can I just 3.
You sure can.
So,
Then,
then 3 over big N is less than epsilon. And if then yeah.
Then you're done, right?
Yeah.
Right? So if 3 over big N is less than epsilon, then 3 over N is less than epsilon for all little n starting at that big N, which gives us this, which gives us this, and you're done. See? It's not so hard.
Convenient. Okay.
Alright, now for B. Oh. We cheated.
Why?
Just barely.
Why?
Yes. Here's where we cheated. We did it the wrong way. We did 2 over the square root of n is less than 2 over n.
Not bad.
No, that's backwards. 2 over the square root of n is greater than 2 over n.
For n greater than 1.
When you take the square root, you get a smaller number in the denominator.
Yeah.
Which gives you a bigger number overall. So no, that proof didn't work.
What?
So I'll prove it real quick and then you'll move on to the next one. So we're proving that the limit of 2 over the square root of n plus 1 over n.
Yeah. Plus
Oops.
3.
That's what we're proving, right?
Mm-hmm.
So 1, let epsilon be some positive number. Okay. And where am I trying to get? Trying to get exactly where she was trying to get. I'm trying to get, therefore, the absolute value of 2 over the square root of n minus 1 over plus 1 over n minus, or plus 3 minus 3 is less than epsilon. For all n from some index onwards. Right? Hang on, I think let's kill
You
this.
missed
Okay.
the first 3
Oops.
plus the minus 3.
Okay. So we know we've done it when we can show that, right? And we showed that when we've shown then 1 over 2 square roots of n plus 1 over n. Right? There's a simplified version.
Mm-hmm.
Let's play with that. What does that equal to? Well, let's get a common denominator. Maybe that will help us think. Right? Multiply top and bottom by square root of n on the left-hand term. Now we got a common denominator. And then we can combine like terms and maybe that will help us see something. Right?
Yeah.
Yeah, see. Oh, right. Yeah.
Now we can get that into something really simple.
That's definitely less than 1 over n.
There we go. And that's definitely less than 1 over n.
Less than, yeah. You don't need to worry.
why is it definitely less?
This term can only make it bigger. Right? So if I get rid of that term, I definitely have something smaller.
And then don't you
How
say
did you get rid of it?
for n?
Is it not true that this, maybe that's true? Yeah, let me do this, and then we'll do. Think that'll help.
I'm still not seeing it.
Looks to me like your sign's backwards.
This is less.
Plug 1 in for
Oh, whoa! My sign is backwards. Thank you.
I was gonna say plug 1 in for n, and it still, it did not.
Yep, good catch. Good catch. We were using the same word logic that we were using before. Okay, so that was taking us back down a bad track. Better not do that.
I just need to redo this first.
Now what? What's that definitely less than that we can simplify?
Square root of n over n.
Huh?
Square root of n over n.
Well, no, but like I want to add this to this somehow. So here, maybe I'll just write it and then
I don't get why that didn't work last time, because n.
we wrote something smaller here and said it was bigger. Look.
Oh, right.
Okay. Good catch on their part.
Smaller.
So this is less than 2 squared root of n plus the square root of n is what I'm seeing in my head. Less than or equal, right?
Plus square root of n.
Replacing 1 with the square root of n. The smallest this can ever be is 1, and it only gets bigger from there.
Okay.
And then I can add those terms. Right?
Great.
And then simplify one more time. I think that's about as simple as we can break that down to.
Wow.
Okay? So that's the first part of the problem. That's always the first part of these problems. Is keep messing with this, getting it less than something that is real easy to work with. This is kind of horrific to work with, but that looks pretty straightforward. In fact, that looks a lot like the problem James already solved, with a small difference. It has a 3 there.
How did you move the square root to the bottom?
What is the square root of 2 over 2? No? Okay, let me rewrite this one more way.
Okay.
Alright?
Yeah.
So, square root of anything over that thing is just equal to 1 over the square root of that thing.
Okay, I see.
Okay. Any other questions on the algebra? Does it all make sense?
Yeah.
So now, as some other scratch work I might be thinking in my head, okay, so I need to find a big N, so that 3 over the square root of big N is less than epsilon, right?
Yeah.
Right.
I need to find the big N that makes that true. And when is that true?
When epsilon is.
Well, let's square both sides real quick to help us think. That gives us this. And then let's get our 1 over n like we like, since you guys are more comfortable using it that way.
Right.
Okay, so line 2. Then by the Archimedean property, there exists big N in the natural numbers such that 1 over n is less than epsilon squared over 9. Right?
Mm-hmm.
Then 3 over the square root of n is less than or equal to 1, oops,
Big N, right?
yeah. So then 3 over the square root of big N is less than epsilon. Alright? Then we put a 4 here.
For all values.
Alright? Any part of this that was confusing? Anything we're still absorbing?
Yes.
I'll
It's
keep
the
that
same
with
thing
that.
James was stuck on.
You're stuck on what?
I'm sure I can figure it out. 2 square root n. Okay, it's this right here. 3 square n. Yeah.
This to this?
Yeah. I don't know.
Okay, so if I have square root of 2 over 2, and that is equal to 1 over the square root of 2, right?
Times both sides by square root of 2.
Okay, maybe that's something. Let me rewrite this side. This can be rewritten as square root of 2 over square root of 2 times square root of 2.
Okay.
Can you see it? There.
Yep.
Where'd you learn how to do that?
Simplify those, huh?
Where'd you learn how to do that? By exponents?
No.
Trick.
There was a proof that came up when I took this class that my teacher did, and I saw him do it that way, so I memorized that's how you do it. Right, Jacob?
Yeah. And I'm sure he saw his teacher do it.
I gotta go.
Thanks for sharing.
Well, I didn't want to just walk out.
Okay, now we're going to do.
Okay,
You got it? It all makes sense?
yeah,
You ready to do the next part?
no,
Well, that's too bad.
yeah, I know.
Yeah, I'll have all scribbles everywhere, huh? Just add a few more to
This is pretty fun.
Pretty fun?
Yeah.
Nothing quite like lighting up the galaxy.
We're trying at least.
You missed Jacob's quote.
I think I heard it.
Frustrated with the proof. So his quote was something along the lines of, and he said it in frustration, which is the best part about it.
It's not even that.
Proving something is like trying to light up the whole galaxy. This is the most random connection of things I've ever heard. I guess it's something that's really hard to do.
Yes.
Impossible.
But I don't know, the galaxy's pretty lit up, I think.
My question is, what am I proving that this limit is?
I don't know. What's that going to
It
converge
just
to?
says that it converges.
Yeah, but what does that converge
Probably
to?
0.
Well, I'll tell you that you're wrong there.
1?
Why 1?
I don't know, it looks like it
Stop guessing
converges
and
to
just think
n.
about
Plug in your infinities.
it. Look,
I'm thinking it'll be n.
how does this grow compared to this?
Extremely slower.
Slower.
Nothing.
Yeah,
N is nothing compared to n squared when you're talking about really big numbers.
yeah.
10 trillion is nothing compared to 10 trillion squared.
Mm-hmm.
What's 10 trillion squared plus 10 trillion? Basically 10 trillion squared.
Yeah.
That's basically all it is. And this is 10 trillion squared. So this gets closer and closer to
What?
1. This is basically the same thing as that,
Oh, okay.
right?
This is how Ariel did it.
10
For
trillion
large
is
values,
even 1/10 of the numbers you'll get.
Yeah,
zero.
he just, 0,
Yeah,
0,
For large values of x, then we know.
that it approaches.
And it doesn't matter in this equation.
Okay.
Let 3 be greater than 0.
Yep, absolutely.
Therefore, by our condition property, 1 over n is less than an epsilon.
Okay.
It's quite a leap from 3. proof.
Why did you?
Dot, dot, dot.
That's all you ever do.
That's not what I said.
Is less than epsilon.
Uh-huh. Okay.
This is so, oh, can I say, okay,
We know that.
I'm just gonna start something
If you're
and,
Stuck with it, get a common denominator. Combine those things together.
well,
Probably
what I
just
wanna
scratch.
do is get rid of the n because,
Look, plus
Well, you
one.
can't just get rid of that
well,
yet,
if I have,
because you have the -1.
Yeah, you got a plus one to make it 0.
Look, isn't
Fine,
that
I'll do
term
that.
-1 just less than n squared over n squared plus 1? Or plus n?
Well, you rewrite it as
is
n
less
squared
than,
over n.
See exactly what she's doing.
can I just write it
This
as
is- that-
n
this isn't
squared
gonna
over
help you
n
with anything.
squared?
Proving that this is less than something.
Well, okay, here's where,
Get common
Oh,
denominators.
then you're gonna say that this is less than that. I don't know how you can say that.
Okay.
I mean, you have to prove that for natural numbers, it certainly seems like it might be the case. But if I have absolute value of A minus B is less than something, doesn't necessarily mean the absolute value of A is less than something.
Okay. Okay, no.
Does that make sense what I'm saying?
No.
Let me give you a quick counterexample. So what I'm saying is, just because the absolute value of A minus B is less than something, we'll say C, that does not mean that the absolute value of A is less than something, which is what you're trying to do. You're saying I have A minus B is less than something, therefore A, if I can show A is less than it, then this is
plus
also
b
less than
minus b is less than c is the same as.
So this does not mean this. And I can give you an example really quick where that's not true. Imagine that we had the case 3 minus -7. What's 3 minus -7? 10. But if we just did the 3 by itself, that's just 3. 10's a lot bigger than 3.
I know, but.
So
it's
getting
still
rid of
less
what
than
we were
C.
minusing didn't make it smaller, it made it bigger. Right?
what are you, okay, what? Look, well, okay, if you have 10 which is less than C, 3
Right.
is
Well,
definitely
that's pretty
less
good.
than C.
So, if I have, oh,
She's right.
yeah, you're right, so let's do it this way. If I can show that 3 minus 3 is less than 0, does that imply that 3 is less than 0?
Okay.
Well, that's the one, sorry. There we go. Yeah, that's even weird. So you can't just, showing that this is less than something doesn't tell you anything about this.
Okay.
So you want to take this whole thing and manipulate it. You don't want to just take a piece of it and manipulate it.
So you're saying get common denominator.
That would be where I would probably start this.
Denominators, okay?
He knows.
Positive 1.
What do you mean I know?
How come you don't just add a positive 1?
And subtract positive 1?
Yeah.
So you get n squared over n squared plus n minus 1 plus 1 minus 1?
No. Just.
You can only add 0. And you
Yeah.
can only multiply by 1. You
Yeah,
can't
if
just
she's following this, then shouldn't that have a plus 1 right there?
No. She's proving that the limit of this is equal to 1.
Yeah.
A
Oh, in her
Hey.
next or the one above should have a plus 1, right?
No! There's no plus 1 coming into this thing.
He's getting confused with the limit that equals 3.
Yeah, just because that other one happened to have a plus 3 here
It had a plus 3 in the AN. This has
in the AN.
no.
So we had a plus 3 and a minus 3 because this was 3 and there was a 3 in there. That was just coincidence.
Okay.
So no, you can't just go around plusing 1 and minusing 1. You can only plus 0 and multiply by 1. Those are the only things that you can do to an expression to not change the value. Okay?
Okay, now.
Add them together. So now.
So now this
Factor out your n.
No, it's equal to that. It's not less than it. Alright, you see what she did? Just cancel out the n squared terms. So from here to here, she got common denominator. She took this 1, multiplied top and bottom by n squared plus n. You did from here to here? Okay. N squared minus n squared minus n is minus n.
Okay.
That's all she did there. Now, I don't know what she did.
No, you also take away a square.
Oh,
That's me, it's not no.
What?
holy cow.
Take away your square.
Let me try and make sense of this. So let's say we're looking at 3 over 3 squared plus 3, right? And you just rewrote that as 1 over 3 squared plus 1.
Yeah.
So you are telling me that 3 over 12
No.
is equal to 1 over
She
10?
meant to take away the square. She meant to take away the square.
No, it's not.
No, that you meant to take away the square. You didn't even see that. You didn't. Like you accidentally kept the square.
Oh, Mom. Okay, yeah, I see what you're saying now. Okay.
Okay, you factored out and then top and bottom.
Yeah.
Okay.
Okay. Oops. Sorry.
Now, is it true to say? Now we have a negative. Oh, it's steps value.
Oh, wow, that came out nice.
Do we know that n is positive?
Hey, look. Yeah. Well, it is positive for natural numbers. And we're only going to plug in natural numbers there. So it's going to be true when we're all said and done. Right now, we're still just playing.
And that is definitely less than 1 over n.
Hold on. Wait.
Which to our property. Yeah, I figured it out.
Therefore, now we plug it in.
What?
Now I don't know what to do. But this.
What are you trying to get? You're trying to get that
I'm
less
trying to
than
get that. Yeah. Okay.
for all n greater than or equal to big N. That's what you're trying to get. So now find the big N that makes that true.
So 1 over big N plus 1. Which is less than epsilon.
So you could do that. You're going to give yourself a little bit of a headache if you're trying to do that. Notice that.
I'm trying to find my index. Right. The bigger this number. Okay. Which is less than epsilon.
Well, you need to find an N that makes that true.
Oh my god. What?
Why the mark?
Okay, keep going. Keep writing.
Okay, so.
Boom! And we're done.
Sorry.
Well, try and hold it in next time. Right?
Yeah, should I write all of that stuff?
If you feel like it's not obvious, then yeah. Whoa! If you're going to write something, write a statement. periods and a black box, and you're good to go. Boom. Is this getting easier?
Yeah.
All right. Jacob, you're up. Unless Mark wants to do one. We'll let him decide.
Yeah.
Oh, number 4 is the one dealing with that weird sequence, huh?
Yeah, for that sequence, number 4,
A,
find
B,
a
C.
different example.
So
Like, just
I'll
plug it in.
give you the sequence.
Huh?
The sequence is
You want to do it? Okay, go do it.
The sequence is K over.
1 over
Just
2,
plugging in numbers.
Yeah, basically.
3, 2 over 3, 3 over 3.
So what's the actual sequence?
This is the
It's-
sequence.
That's the sequence, but there's a way of deriving it.
It's K
Oh,
over
Is
J
that
plus
what you
1.
have to do?
It is n equals j times j plus 1 over 2 plus k, where k is in between 1 and j plus 1.
Jim, is that all the second element?
You just have all this stuff in
What?
your
Is
head.
that all the second element?
Yeah.
I don't understand the question.
You look
I don't
better.
have comments.
It's literally getting better as we go.
Wonderful.
Beautiful.
You still don't have comments.
We should leave that definition of the all year.
Or you should just memorize it.
I have memorized it already.
Did you just say you have memorized it?
Look at it real quick.
No, j times j plus 1 over 2.
Then what's
Oh, sorry, yeah. Wait.
this? What's this? Because I remember this.
No, there's k over j plus 1
Is this it right there?
is the term
Example
when n
2.3.
equals, yeah.
It's that right there.
Oh,
It wants us to go in our textbook.
yeah, for A, but that's,
A and the sequence equals
this is different.
Okay, where's the
So,
A.
find example 2.3.
Look,
Equals k over j plus 1, and n equals
and n equals
j times j plus 1 over 2,
Yeah.
plus k, right?
where k is between
No,
1 and
not.
Over, yes.
n equals, where does n equal? J times j plus 1 over 2 plus k. Where 1 is less than or equal to k is less than or equal to j plus 1.
1 is less than or equal to k. Which is less than or equal to what?
K plus 1, or j plus 1. Yeah. So what are they saying here?
Jeez.
They're saying, look, pick an n.
Okay. 1.
Well, let's pick a different
4.
one. Where's the marker?
There.
Alright? Let's pick, let's see, how many did you do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's do 11, since that's how hard. Let's say n equal 11. What are the j and the k that we can put in here that satisfy this condition that give us the number 11?
Well, make j equal 1.
No, j is equal to 4, and k is going to equal 1 is the number that make it work. Remember, k has to be less than or equal to j plus 1. And it turns out the numbers that do it are 4 plus 1 is 5, divided by 2, plus 1.
Okay, wait.
Right?
Wait. What are you even thinking? So these are our terms and conditions for our k.
What?
K has
We
to be-
need to find j and k that make this equal to 11. Where, so maybe there's some confusing stuff down here, get rid of that, get rid of that, get rid of that. Okay, so you pick any number n you want. You picked 11, right?
Let's start off.
This tells us what j and k have
We are
to
starting on
be,
A, right?
No, this isn't A. This
and
is
they have to equal 11. And the conditions of j or k are this.
Yeah.
K has to be, k
K has to be less than
I know.
J plus
K
1.
has to be greater than or equal to 1 and less than or equal to J plus 1.
Yeah.
So you can start plugging in a whole bunch of numbers. You can start guessing numbers to your heart's content.
Our K is 1 and our J is 4.
But whatever you're guessing, make sure that you don't pick a K bigger than J. Or more than one bigger than J, right?
Oh my goodness.
So what did we say our J
I'm
was?
an idiot.
4?
So I'm saying in this case, if you want to get 11 out of here, the J that you're going to use is 4. And the K that you're going to use is 1.
And if you want to get 12,
Then it would have been different numbers.
Same
Same thing,
thing,
but
too.
K would have been 2. Yeah,
and then 13, K would be 3.
right.
Okay.
Yo,
So 1/5.
So,
Or 11th term.
here's what, so that makes it true. So we had J equal to 4 and K equal to 1. Those were the J and K that made this work.
Right.
So then we're saying our 11th term is equal to K over J plus 1.
Why are we even dealing with this?
So our 11th term
I know.
is
What I'm
that.
saying is this seems stupid. Like,
So here's how you get the J and the K from the index. And then once you have the J and the K, that tells you the nth
I'll
term.
show you.
I
why
know.
we
I'm
want
saying why are there conditions of a sequence?
How else are you going to capture the sequence?
Jake, imagine you're writing
This
a
isn't-
program for leveling up. Boom.
Well, I don't know about that, but you're trying to capture the sequence. As infinitely many terms I can capture it.
sequence.
Yeah, it's an awesome sequence. What do you mean?
Okay, so what does it mean to find the second index?
Jacob's going to take us through it. He's going to start with A. He's going to walk us through what A is. I don't know what it means. It's not my job to do it.
What is the first question?
My job is to assign homework.
What are the terms
You're
at
just
A
finding
sub
at
10?
10, 20, and 30.
20.
So,
when n is 10, n
It's
is
1.
Sure.
Hopefully.
So A sub 10, A sub 20, and A sub 40? Was that
30.
30.
So
Okay.
It's 4.
if A is
Oh,
10,
4.
well, first let's just do it. N equals what? J times
J plus 1
plus 1.
over 2 plus K. Where 1's less than or equal to K is less than or equal to J plus 1.
And AN is equal to K over J plus 1.
Yeah, and then AN is equal to K over J plus 1.
Can't control my body when I have
Two.
shivers.
J over K plus 1.
K over J plus 1.
Huh?
It doesn't make me.
And your K is less than or equal to
Make
J
me.
plus 1.
Jake,
Yeah.
why does it do that? I don't know.
Okay, so
So you're finding A sub 10.
since K has to at least be 1, then J has to be 3 because we learned that 4, that will get to 10, and we're trying to get to 10. So for it to equal 10, it equals 3, 4, 2, so that's going to be 6 plus 4. Right?
Yeah.
Oh, wait.
Yeah, you're right.
No, K can't be 4 because is that equal to as well?
Yeah.
Oh,
Oh,
okay.
did I not tell you that?
Sorry. Okay, there we go. So the term in that sequence is J is 3, so and K is 4. So 4 over 4.
Yeah, so the 10th term of
Wait,
the sequence is
wait,
4
wait,
over
wait.
4.
You just said, oh, J plus 1. Okay, never mind.
Okay, and if n is 20, is that what it was?
Yep.
Okay, so 4 gets us 10, and the greatest we could get is 5 on that 10, so 15. So we're gonna have to try 5. 5, 6, 2, that equals 15.
Plus,
Yeah,
It's
you're
getting
right.
you
You're
over.
right. Your equation's weird. You're saying 20 equals 15.
No, he's saying 30 equals 15.
No, he's saying 20 equals 15. It's not what he's trying to
You
say,
need to add
but
the
it's what he has
K
written up
before
there.
your equals.
Okay.
I mean, you have it in your brain. It's just
There you go.
Plus I'm trying to do 25.
Why are you trying to get to
So
15?
K equals 5.
Oh,
K equals 5. J equals 5.
No, J equals Oh, 5. Yep, sorry.
So 5 over 5.
But the sequence looks like 5/6.
Yeah, it's 5/6.
Because it's
J
K over
plus
J
one.
plus 1.
J plus.
Oh,
I actually counted it out. I didn't go through this process.
And you got 5, 6?
Yeah, I got 5/6.
There you go.
good job, that's organized. 30. Okay, so this got us to 15. Problem 6 times 7 would be 40.
3 times 7. Do half of it.
Huh?
3 times 7 is 21.
Over 2.
Why do you want 21?
21 plus 7 is only 28. It's not 30.
Are you guys trolling me?
I don't know what you're trying to say.
Everyone's gonna have a different way if you're thinking of where they're at.
I'm thinking 6 and 7. But
It's
6
what?
It's 42.
That
21.
one.
Okay.
Oh! You're multiplying instead of dividing, which is just stupid to do when you're doing math in your head. Divide, then multiply.
So 7 won't work, 8's gonna have to be our work. Because 21 is
6
less.
won't work.
Huh?
6 won't work.
6 won't work. 7 might work. Or 7 is what we're gonna
7
have.
times 8
Yeah,
is
7 will
66.
work for sure.
Divided by 2 is
Okay, 7 times 8 is 56.
7 times 4. Make the math easy for yourself. Don't do 7 times 8 divided by 2.
Shut up!
You're 7 times 4 in your head. It's fine if you have it written out like that.
28.
I'm just saying, stop doing 7 times 8, then dividing. Divide first, then multiply. Save yourself the work.
J equals 2, J equals 7.
2
So
1/4.
2 8s. Is that what they want?
2 8s, yes. Not 1/4. 2 8s.
5 6. So
Boom.
We have to show our work.
1/4, but.
yeah. We have to show our work.
No, you just had to figure, you just had to say a sub 10 equals 4 over 4, a sub 20 equals 5 over 6, a sub 30 equals.
So what's the point of the exercise?
Well, that was just A to get you comfortable with.
Find the second index.
The
Wait,
sequence.
erase that.
So now what?
Erase.
Part B. Well, that was part A. Part B is what?
You guys mean?
Yeah, someone read it out.
Find the second index n for which n a sub n equals 1/4, and the fourth index n for which a sub n equals 1. Look, what does it mean for second index? Does that mean the next time?
So-
Find the second n for which the.
Let's see, he said the second index where it's equal to 1/4, right?
Yeah.
So the first index where it equals 1/4 is 1 over 4.
Right.
What's the second place?
Right here.
2 over 8. So you're done.
Wait, are we
So
sure about
what
that?
would be
Yes,
the index?
positive. Okay, and then what was it? The fourth index where it equals 1?
So,
Right?
10.
The fourth, yeah.
10. Ah, you're done.
No, that's not. Oh, yeah, 4.
Alright, so the two indexes were 30 and 10, right?
Yeah.
Okay, that was easy.
Easy. Okay. For J and odd natural numbers,
the worst. You
show that AN equals 1/2.
You should download a different one.
Why does AN
This
equal
is,
number? AN is this sequence.
This is software.
Yeah, so now you're about to see something crazy.
And you use the
Anytime you force J to be an odd number,
Yeah.
that a sub n that comes out is a half. It might be this half, it might be this half, it might be whatever half comes after. So anytime J is an odd number, then the term in the sequence is just 1/2.
J's an odd number.
Scroll up.
Yeah.
Right here.
No.
It's 2 8s.
Well, what?
J's an odd number right here.
No, J was 6. Oh, you're right.
7.
Let me think. Let's read that one more time.
Oh, it's a different set.
Oh, you're plugging into different numbers. You're plugging into, not that, but I don't have the problem in front of me.
Here, check.
You're
Sorry.
plugging
Yeah, so into whatever that formula is.
in. Your K is
So
turning
for
into
J, an odd natural number, set n equal to that, and show that a sub n equals 1/2.
Or we have to prove this?
Yeah. So make j an odd number,
For any odd
and
number.
show that that makes a sub n equal to 1/2. So if n equals that expression where j is an odd number, then a sub n equals 1/2. So this is a way to find all the indices where a sub n is equal to 1/2.
So confused.
Look at it. When we were setting n equal to this, that was how we got the index, right? Now we're saying get the index this way. Okay. So plug in an odd number for j, which gives you an n, right? Then they're saying a sub n is going to be 1/2.
That's what they're saying.
So it's either going to give you the 1/2 term, or the 2 4s, or the 4 8s, or the 8 16s, etc.
Okay, prove that this series.
So
is
maybe do an example real quick. Pick an odd number, plug it in there to show this in action.
1 times 2 over 2 plus 2 over 2.
What does that equal?
It equals 1/2. Or sorry, it equals 2.
It equals 2. So we're saying the second term in the sequence is 1/2. Oh, what do you know? Pick another odd number.
What? 2. It equals 2.
No.
N-
Yeah, 2.
N
N equals 2.
So
You're proving that anytime j is an odd number, that gives you an n, right? Any n that you get when j is an odd number, then a sub n equals 1/2. So a sub 2 equals 1/2. In other words, watch, plug in 3. When you plug in 3 to this, what do you get?
3 times
6 plus 2 is 8. So we're saying the 8th term in the sequence is also 1/2. 1, 2, 3, 4, 5, 6, 7, 8. Ah!
Oh, we're still dealing with this and.
Yeah, same n, we're just calculating the index n a different way now. Instead of doing n equal to this, you're doing n equal to that. So you're replacing your k with a j plus 1 over 2. We're saying anytime that you pick an odd number for j, then a sub n comes out to 1/2 if you calculate n this way.
Okay, how do you write out the top line of the proof? Prove that in this set,
Observe.
Prove n
For
okay, we don't need this anymore.
It's okay, you have
and
the
last
in
thing
there.
numbers. So I already said let J be on.
Well, you might want to write that as your first part of your proof. Might help us. Here we go. 1, let j be an odd number. Or let j be odd. 2, what does it mean for j to be odd?
What's the definition of odd?
I'm thinking that you can improve this by way of induction, but
What's the definition of odd?
it's not going to be n plus 1, it's going to be n plus 2.
You don't have to use induction for this.
What's the definition of odd?
What is the definition of odd?
2a plus 1.
There exists an integer a such that 2a plus 1 equals j. That's what it means for j to be odd.
No, that's for every. What is there exist?
A backwards
The
e.
E.
Yeah, then there exists.
There exists.
You don't start out sentences with math symbols. Then there exists some integer, call it whatever you want.
Integers. Integers are is a z.
There exists. No, you do that. Integer.
There exists a.
Then
integers.
there exists in integers. Then there exists an integer a. Oh, there we go. Such that what?
2a plus 1 equal to j.
Odd.
Is equal to j.
That's what it means.
That's what it means for j to be odd. If j is odd, then you can find some integer a such that 2a plus 1 equals j. For example, is 7 odd?
Yes.
Yes. How would you prove 7's odd?
3 times 3.
2 times 3 plus 1 equals 7. Is 6 odd?
No.
No, there's no integer a I can find such that 2 times a plus 1 equals. Does that make sense?
Yeah.
Now use a lowercase j because that's what you have in the problem.
Lowercase g's are fun.
They're fun.
Fun. Okay.
Alright. Okay. Okay.
We're gonna have to use this.
Yeah, you're going to have to use that. So now we know that j is odd. So j can be expressed as 2a plus 1.
Oh my goodness, that's
So we can just substitute it.
Sure. Isn't that what you can do when things are equal? Wow, we are not going to get through very much homework. Jeez, this class is almost over.
Yeah, that's kind of weird. Oh, no, it's not.
Oh, is that clock way off?
It's
Yeah.
11.
No, it's
See,
11.
You're reading. You're reading wrong.
There's a big blur over that. Is that not?
No, it's off. It's barely on. Oh, nope, nope. It's right.
Yeah, that clock says it's
It's right.
a little after.
An hour is supposed to be done.
Oh,
Yeah.
I'm horrible at reading. So I like that at thinking it was almost noon.
Alright.
Okay.
Okay, what does that equal?
Okay.
I want to substitute on that.
Why did you do? Why are you getting 2 plus?
I'm substituting.
Why do you have 2a plus 2?
Because he added the 1.
Because 2a plus 1 is j.
Oh.
So 2a plus 2 is j plus 1.
What are you doing?
Follow?
So, let me make sure you understand where you're trying to get. Do you know where you're trying to get? Trying to get that a sub n equals 1/2, right? What do you know that a sub n equals?
And 1/2.
No, what do you know it equals? You're trying to prove it equals 1/2.
Equals this.
Okay, so you're also going to have to use that information.
Couldn't
Yeah,
you
but your
just
K is
combine
not
those
K,
two
your
up
K.
first?
Oh,
Oh,
yes,
yeah,
it
I
is.
can do that.
But what is k?
Yeah, he's going to have to figure out what his k is.
How
Yeah,
did
It's
what I'm
gonna
trying to
involve
get to.
A, obviously.
Yeah, it is. So I'm not saying anything you're doing so far is wrong. I'm just saying remember that you also need to use this information because you're trying to ultimately show that this is 1/2. Right?
Okay, what is K?
Yeah, that's what you got to figure out from over here. K is some number between 1 and j plus 1 such that this is true.
Whoa.
I mean, should kind of be popping out again.
K is half of an even number.
So let me see what you did.
Right here?
Well, sorry, let me look at this for a second. So you plugged in there, right? And you plugged in there, right? And then you simplified, right? Okay, so what's your K? And what was your J?
K. I don't know.
You don't?
This is my K. Is this
Alright.
my K?
Hey, if you're stuck, here, use this. And then work with it. You can substitute it for A, and you can use this and this to figure out what K equals if you're stuck there.
Look. Doesn't that equal K?
There you go. That's all you need.
That's what I said. I said
Oh.
doesn't that equal K?
So what's K?
In terms of
A
A.
plus 1.
Yeah.
In terms of A, it's this.
There you go. 4, then K equals A plus 1.
then you're trying to get it to.
So you have J and you have K. So now what's A sub n?
What is J?
Everything is
Wait.
1.
So
A equals 1.
So now we need to bring it up to right here again. Right here.
Yeah, so A sub n equals
Equals A plus 1 over 2A plus 1.
Plus 2.
look A sub n again. It's J plus 1. See that?
Yeah.
Okay. And that's what A sub n equals. You're not
I'm trying
multiplying.
to prove that A sub n is going to be 1/2.
Break it up.
You're done.
That is pretty cool.
I didn't know that we were still dealing with these things.
You're still on problem 4.
Yeah, we're still on problem 4. Alright, proof. A and n does not converge. Is that proving? I guess that's the sequence.
alternating.
Prove that this sequence does not converge.
Not alternating. Just trying to converge. Someone keeps checking it.
Wait, prove it doesn't converge. Can't we just find the counterexample?
No, you have to prove it doesn't
Take out
converge.
1. No, 1. No, 1.
One.
I guess
I'll
alternating.
slower.
Should I let you do this or should I take over?
This is one I actually had a really hard time with.
Sure. Alright, I'm just gonna prove it real quick. So let's prove that the limit of this does not equal 8. 1. Assume, by way of contradiction, that the limit of A sub n is equal to A, right? Then there exists some index big N in the natural numbers such that A sub n minus A is less than 1/2 for all n greater than or equal to n. You good with that?
Then there exists n such that.
Yeah.
Wait,
Less than 1/2.
there exists n such that.
Do you mean epsilon over 2?
No, I mean 1/2. Remember how you do it when you're disproving. Did I erase the...
Oh, you choose your epsilon, right?
Yeah.
And you find an index where it's
You
not.
choose your epsilon and you show that for any index, this isn't possible. There's no index I can start at big N, so that this is true. So I'm assuming that there is some index big N that I can start at where this is true. And we saw it leads to contradiction. So it can't be true. Does that make sense?
Okay.
Math annotations.
Okay. So 3, here's the way I say it. 3, then A sub n1 equals a 1/2, and A sub n2 equal to 1 can't both be true for n1 greater than or equal to n and n2 greater than or equal to n. In other words, if this is within 1/2 of A from some index onwards,
Yeah.
then I shouldn't be able to find an index afterwards that gives me 1/2 and another one afterwards that gives me 1.
Right.
Oh wait, that's not a problem. Let me switch this to 1/4. Sorry.
I'm confused
Yeah.
on
if a sub n is always within 1/4 of a, then it can't be 1/2 and 1. Both those numbers are not within 1/4 of any number.
Right.
Right?
Mhm.
Their gap is 1/2 apart.
Their gap is
Gap
1/2
needs to
apart.
at least be 1/4 apart.
Right?
That was an easy proof. Why didn't we do it?
We're not done. I need to show that this can't happen now.
We just did right there. Term 1 and term 2.
Wow.
Well,
Okay.
we'll use previous knowledge that we have in this proof. But make sure we understand this. Look, if AN converges to A, then that means here's A wherever it is. Let's see. Here's 1, here's 1/2. And I'm saying it has to be within 1/4 of A. So let's see. What are all the terms within 1/4 of 1?
Like,
That's all the way over here to 3/4, right? And then going up to 1/4. What are all the terms within 1/4 of 1/2? That's all the way up to 3/4, not including 3/4, and all the way back, like that, right? So these are all the numbers within 1/4 of 1/2. These are all the numbers within 1/4 of 1. Are there any numbers that this is within 1/4 of that this is within 1/4 of?
no.
No. So, I'm saying there comes a point where AN is always within 1/4 of A, right?
Mhm.
And I'm saying notice that 1/2 and 1 aren't both within 1/4 of A, doesn't matter what A is.
Okay.
So that means A sub n cannot be both 1/2 and 1 starting at this index.
Okay.
Does that make sense? And then I'm going to show that I can always find an index where that's true, right? Using our knowledge from the previous problems, we know that. What were the indexes that did it?
10 and 30.
So I'll just write out what I did right here. Can't both be true for n on an integer than n. So I said, for let j equal 2n plus 1. Sorry. And k equal n plus 1. Doing the last thing that Jacob just did. What did he do over here? He said when we do j equal 2a plus 1, then k equals a plus 1, and j sub n, and then a sub n equaled 1/2.
Right.
Right? So notice all I did was switch a's with the index, right? So let j equal that and k equal that. Comma, and let n sub 1 equal 2n squared plus 4n plus 2. Why did I do that? I was probably simplifying this, but we'll just plug into this directly. So let big N equal, when you plug in J and K, what do you get? You get whatever Jacob had written right here. Switch A's for N's, right?
Mhm.
And simplify that one more time. So I'm rewriting this, but with N's instead of A's. So let J equal that, K equal that, and N1 equal. We get the 2's cancel out, so we got n plus 1 squared plus n plus 1, right?
Yeah.
Which we'll notice is bigger than n. obviously 5, then A sub n1 is equal to 1/2. Right? If I make n1 my index, where I plug in my j and my k, then A sub n1 equals 1/2. That's what we just proved in that part. There's a reason that this problem flowed the way that it did.
Okay, that worked.
Okay?
So, we showed that there was still an n1
Greater.
bigger than n, where A sub n1 equals 1/2. Now we need to show that there's an n2 greater than n, where A of n2 equals 1. Okay? So, 6. Next, let j equal n plus 1 and k equal n plus 1. I think that's what I did. And let n2 equal
Why can't you say let j equal n plus 1?
I'm going to plug j equal to this and k equal to this in the formula. The only restriction is that both these have to be greater than or equal to 1, which they are, and that k has to be less than or equal to j plus 1, which it is. So these are perfectly valid values. I'm just saying when I assign these values to them, we're going to get 1 out.
It's less than or equal to because of the.
So then n2 is equal to, when we calculate the index, right here, is what we're plugging in to for n2. What do we get?
Okay, what?
We get, no, when we're plugging for n, we get j
N plus 1.
times j plus 1
Plus 1.
This goes N plus 2.
over 2, right? Plus
N plus 1.
k. And we'll still simplify.
You're not gonna want your k to be n plus 2.
Let me think. Oh, no, I want my j to be n.
That's
Sorry.
the same thing.
So this is n and n plus 1. Oops. Good catch. Because obviously those are the ones that are going to give me a 1, right? If j is equal to n and k is equal to n plus 1, then when I plug it in for a sub n, I'm going to get 1.
Over n plus 1.
Anyways, so there's my j, there's my k, right? And then let's see what we get. We're going to get, well, it doesn't matter what that equals. The point is that is bigger than n, right?
Yeah.
That's all we care about.
Okay, so will you go back and show me why you said J's?
Yeah, just one sec.
n2 bigger than n.
A sub n2 is equal to, maybe we'll say n plus 1 over n plus 1 is equal to 1 and n sub 2 is greater than n. Okay,
What is that?
now we're done. So let's go over the logical
Contradiction.
time. Huh?
Where's
Oh,
the
thank you.
contradiction?
Oh.
Oh, because you said they can't both be true.
Right.
Okay.
Contradiction. Therefore, it can't be true. So let's go over the logic one more time. Okay. Assume by way of contradiction that this thing converges. Right? If it converges, then there has to be some index n for which the distance between it and what it converges to is less than a fourth, right? So if whatever this distance is always less than a fourth, then that distance can't contain both the numbers 1/2 and 1. Right? So, it can't have this and it can't have this. We're going to show that it does. Yeah, for two indexes that are greater than n, right? Because this is true for all indexes greater than n. So if we can find two indexes greater than n that make that true, then we disproved it. You with me there? So now we just need to find an n1 and an n2 that make this true and make this true, and we're done. So let's start by finding an n1. Well, we already know how to make the c equal a half. We set j equal to an odd number, and k equal to whatever that a was plus 1. Exactly what Jacob did over there.
Right.
So we know that that will give us 1/2 out of a sub n, but the question is that index bigger than big N? So we let n1 equal whatever you get when you plug those in,
What do you mean?
the index. Here's your index.
Why'd you square it?
I just simplified it, so you had it right here, and I just simplified this and plugged it in. So 2's go out,
2.
Right.
Squared.
so n plus 1 squared plus n plus 1. I just rewrote this. So then our index that we're talking about is equal to this, which is obviously greater than n, which is all we were trying to show. So we showed that n1 is greater than n,
What are we
and we
trying
know that a at n1 equals 1/2 by our choice of j and k, right? So we found an index, n1 bigger than n, where a sub n1 equals a half.
Right.
We found one.
So now we find.
Now we need to find an
greater
index.
than-
Exactly. We need to find an index n2 greater than or equal to n, where a of n2 equals 1.
Wait, wouldn't it have to be greater than or equal to n1? Because it has to be next in the sequence.
No.
No. It just has to be within here.
Yeah.
It has to be greater than or equal to n. If I can find two indexes in here that it's impossible for them to be in here,
Makes sense.
then we're done. Contradiction. So now I need to find an n2 greater than n, where n2, a at n2 equals 1, right? When does this equal 1?
When they're both.
When k is equal to j plus 1, right? So let j equal n and k equal n plus 1. So let k equals j plus 1, right?
Why do we want j to equal n again?
We're just picking some big number for j to equal, so that the index, when j equals that, is bigger than n.
Okay.
Right? So I pick j equal to n and k equal to n plus 1, so that n2, the index, is equal to j times j plus 1 over 2 plus k. So that this index is bigger than n now, right? That's why we chose j to be n, because we wanted this index to be bigger than n. There are other numbers that we could have picked for j. There's tons of numbers that we could have picked for j. That's just the easiest one. Alright? We could have set j equal to 10,000 and k equal to 10,000 n plus 1. So j could have equaled 10,000 n, and this could have equaled 10,000 n plus 1. Still would work. But this one also happens to work. We checked it. We let j equal n, k equal n plus 1, and then our index equals something bigger than n. Okay. So now I got n2 is bigger than n, and I know that a at n2 is equal to 1. So I found an index n1 bigger than n,
Why did you write it as that?
Where it equals 1/2. To help you see it, that we're using this formula.
Okay.
I didn't bother using that here because we already proved that when you use your index that way you get 1/2. So I didn't re-spell it out when I did the 1/2.
So what we did was, we knew that A1 was 1/2, and we knew that A2 was 1, but we needed to find our indexes that were greater than our original n. We need to find index 1 that was greater than n, and we need to find index 2 that was greater than
What we were showing is that it's impossible for this n to exist. We're showing that there is no index in the sequence I can start at, so that these terms are always within 1/4 of any number. Because eventually we're going to get a 1, and eventually we're going to get a 1/2. Doesn't matter how far down you make me start, I'll eventually find another 1, and I'll eventually find another 1/2. So, doesn't matter how big of an n you pick, I can always find a bigger index where I get 1/2, and a bigger index where I get 1.
Okay.
So this thing can't converge, because you can't even guarantee me it's less than 1/4. Because I can find two things that make it impossible for it to always be less than 1/4. That make sense? Okay. Gonna be able to reproduce this on your homework?
Yeah.
Well, you better if you
I'm
want
not
to stay
gonna
in
write
class.
off my notebook so that I can watch the video and make sure I can.
Yeah, I really gonna watch this video.
Good. Watch it 100 times. Give me
Well,
some
I'm
views.
gonna go watch
Make
the
this video on the test. See how you can stick to it.
Okay, let's do the next one. If the limit of a sub n equals a, which is positive, geez,
I think I have a new theory. If it's still wet a little bit, it erases it.
What?
It erases it. Well, I erased it.
yeah, that was a worse marker. That was good to begin with. Alright, let's do it. Alright, if the limit of a sub n equals a, and a is positive, then there exists a natural number such that a sub n is greater than 0 for all n greater than or equal to n. If the limit of a sub n is equal to a, comma,
Whoa.
then there exists some natural number n
James, did we do C?
Yeah. It's the opposite.
such that
It's relatable.
I lived with
Yeah, it's supposed to be C.
For the sequence. Show that there, Anthony.
Alright, so what are we saying? We're saying if this sequence converges to a positive number, oh, I didn't say, if a is greater than 0 and the limit of a sub n equals a, but this should kind of make sense, so let's make sense of it. So a is a positive number, it's not 0. A is a positive number.
Yeah.
Okay? With me so far? A is a positive number. So if I have a sequence that converges to a positive number, then there comes an index in that sequence, a point in that sequence, where all the terms are positive. From there on out.
Yeah.
Right?
Okay.
So I might have some sequence, maybe it starts out like -3, -2, -1, 0, 1, 3 halves, I don't know, 4/3, 5/4, and maybe it continues like that, getting closer and closer to 1. See what I mean?
You're going to
I just pick some random thing that starts out negative.
You skipped problem 5.
I did?
This is
Yes.
problem 6.
Oh, I didn't do problem 5. Oops.
What is up with you?
I don't know. So we're doing problem 6.
Okay.
Okay. Maybe I didn't assign it in homework. Should I assign it?
Yeah.
1 through 9.
1 through 9.
Weird. Alright, anyways. The point is, if the sequence converges to a positive number 1, then there comes a point in the sequence, namely starting right here, such that from that point on, all the numbers are positive. That's what we're going to prove. So if the sequence converges to a positive number, then there comes a point in the sequence where from that point on, all the numbers are positive. Make sense? Okay. So, what do we know? Well, first off, let's get our epsilon. Let 0 less than epsilon less than a. Pick some number that's positive, that's still less than a. A is a positive number, we know that we can find a number smaller than it, right?
But
A is a positive number, sorry, it's written up here. So let epsilon be some number smaller than a that's still
Why does
positive.
it have to be more than
Because I'm trying to show that a sub n is greater than 0 for all things from an index onward. So I need to find that index where a sub n is greater than 0 from that index onwards. And it's going to be the same one that makes it converge to epsilon. Or write it out, then explain it. Maybe that will help. So 2. Then there exists big N such that the absolute value of a sub n minus a is less than epsilon
Did we just use our community property?
for all n greater than or equal to n. No, I'm just using the fact that this thing converges.
Oh,
I mean, we kind of use the Archimedes property to get epsilon. We're saying pick a positive number smaller than a. Archimedes property says we can do that. Okay. Now, the magic of the whole proof is I need to show that a sub n in this case is now greater than 0. So I'm saying from this point onwards, as long as epsilon was less than a, then every index that makes this true also makes a sub n greater than 0. Okay? That's what my claim is, and that's what I need to show. So let's see. A sub n minus a less than epsilon, we can rewrite that as then negative epsilon is less than a sub n minus a is less than epsilon, right?
Yeah.
Plus a to both sides, which gives us a minus epsilon is less than a sub n is less than a plus epsilon. The right hand side of this kind of doesn't matter. Since a is greater than epsilon, then a minus epsilon is greater than 0. Therefore, 0 is less than a minus epsilon is less than a sub n.
Yeah, I see why you.
For all n greater than or equal to n. There's the proof. I should have rewritten that right there. For all n greater than or equal to n. So let's make sense of it one more time. So we're proving if a sub n converges to a positive number a, then there has to be some index in the sequence where the sequence is positive from that index onwards. Good with what we're trying to prove?
Mm-hmm.
Okay. So first thing I said is pick some number smaller than a that's still positive. Since I know a sub n converges to a, then there has to be an index n where a sub n minus a is less than epsilon from that index onwards. Right? And it just so happens that this being true also means a sub n is positive. That's what I'm showing next.
Because
So,
epsilon's bigger than 0?
because a minus epsilon is bigger than 0. A minus epsilon is bigger than 0 is what we're going to have. So if this is true, then this is true, right?
Mm-hmm.
Add a to both sides, then this is true. A minus epsilon is less than a sub n. Or a sub n is greater than a minus epsilon. This is a positive number. How do I know this is a positive number?
Epsilon's positive. And it's between 0 and a.
Because a is a positive number.
A is greater than epsilon.
Oh, yeah.
That was our definition of positive.
Oh yeah. Okay.
Right?
Right.
Oh, sorry, this is our definition of positive. A minus epsilon greater than 0 is positive. This is our definition of A being greater than epsilon. A being greater than epsilon means A minus epsilon
It's positive.
is greater than 0. That's exactly what that inequality means. So we have A minus epsilon is less than A sub n, and we know that A minus epsilon is also greater than 0, so A sub n is greater than 0. That's the logic there. You see it?
Mm-hmm.
Clicks? Nice, easy proof. Didn't have to do any real fancy stuff. Next one. the limit of a sub n equals L, and there exists an index n, such that for all n greater than or equal to n, bn equals an, then the limit of bn also equals L. They converge to the same thing. Okay. This one's just going to be, oh, I can't write it. Just do this. All right, we're going to prove.
Use the comparison one before quick.
Oh, it gave me that hint. Prove that
Reviews and testing.
if the limit of a sub n is equal to a, and b sub n is equal to a sub n, for all n greater than or equal to some index big N, comma, then the limit of whatever we're doing, b sub n is also equal to L. Sorry, that's supposed to be cursive L. Right?
So, you wanna explain what B sub
What do you
n
mean it's
equals
also
A
equal to
sub
that?
n?
Okay.
all-
Oh, sorry. This was supposed to be an L. Okay. So if I have some sequence a sub n that converges to L, and I know that b sub n equals a sub n, starting at some index. So they're different, they're different, they're different, they're different, they're different, and then we get to a point where they're the same, and they're the same from there on out. Good? So, if a sub n converges to L, and b sub n equals a sub n, starting at some index, then b sub n also converges to L.
But how is that ever going to happen? When is this sequence going to, at some point, be the same exact sequence on?
You're trying to think about representing in a sequence with an equation. A sequence is just numbers. Right?
Okay.
Pick two sequences pick a sequence, change the first 100 terms. You got a different sequence, but from some index onwards they're the same. Just two sequences. Good? Alright, so let's prove it. Alright. 1. Since the limit of a sub n is equal to L, well, that's probably not what I want to say. We just want to use the comparison limit directly. Do you remember what the comparison limit said?
It's if the limit of A converges to A, and the absolute value of Bn minus B is less than or equal to the absolute value of An minus A at some constant, then Bn,
Well,
and the limit of Bn also
I
converges.
thought the comparison limit was if an converges and is less than.
I don't want n. Okay, so if an converges to A, if c is a positive number, and if the absolute value of bn minus b is less than or equal to c times the absolute value of an minus a for all n greater than or equal to some index n, then the limit of bn equals b. So let's see, if the limit of an equals 0, if c is a positive number, and if there exists big N in N such that that is true, then the limit of bn equals b. You understand all that? Okay, so now let's use it here. observe that the absolute value of Bn minus L is equal to the absolute value of An minus L is less than or equal to the absolute value of An minus L for all n greater than or equal to n. Right? From some index onwards, An equals Bn.
Okay, what are you doing about your constant?
Oh, sorry. How's that? Then, by comparison lemma, the limit of Bn is equal to L.
Ah, that was easy.
Yeah, nice quick proof with the comparison lemma. Any questions there?
Why are you doing Bn minus L?
My question is, why do you have B?
I'm trying to prove
equal?
that the limit of Bn is equal to L.
So how can you
Comparison limit. To show that Bn converges to B, you need to show that the absolute value of Bn minus B is less than or equal to some constant times An minus A from some index onward.
Okay.
So, from some index onwards, the Bn equals An, right? So this is equal to this.
Mhm.
Okay.
Is less than or equal to this. By the comparison limit, that converges. That converges to that.
It doesn't.
B converges to B.
You have the comparison.
Yeah. The comparison limit finishes it off for us. Good?
Mhm.
Alright. Think we have time for one more?
8.
I'll let you pick whichever one you want. You want 8, you want 9, or do you want 14?
9, obviously. Just kidding, just kidding.
No.
Prove that the Archimedes property. Will you just tell us what 9 is even trying to get us to think?
Yeah, I don't understand what we're trying to
Because
do.
that seems like
So, one direction.
It's better.
No. So the Archimedean property is true. Remember, we proved the Archimedean property.
yeah.
So the proof of the Archimedean is true if and only if the limit of 1 over n equals 0. So assume the Archimedean property is true and prove that the limit of 1 over n equals 0. Okay, you already did that. Now, use the fact that the limit of 1 over n equals 0 to prove the Archimedean property.
So we have to go back and watch how you prove the Archimedes property.
So maybe we'll just do it real quick.
No.
Well, you'll watch me do it, then don't look at the video when you go and do it. See if you can figure it out yourself. Or you're welcome to clog your ears and say la 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 la.
I'm looking at it.
Yeah, stare close. Okay. What was I looking at? 9? Alright, so we're going to prove that if the limit of 1 over n equals 0, then the Archimedean property. Alright, so 1. Let the limit of 1 over n equal 0. And let a be any real number you want. Let a be any real number you want. Sorry. And let epsilon equal 1 over a. So remember what the Archimedean property is. The Archimedean property is for any really, really big number you can pick, I can find a number bigger, a natural number bigger. Right?
Mhm.
So I'm saying a is your really, really big number. And I'm going to find a natural number bigger than a using the fact that the limit of 1 over n equals 0. Okay? And here's the epsilon I'm going to use. So since the limit of 1 over n equals 0, 2, then 1 over n minus 0 is less than epsilon for all n greater than or equal to big N. Sorry. Then there exists big N numbers such that 1 over n minus 0 is less than epsilon for all n greater than or equal to that variable, right? Then the absolute value of 1 over n minus 0 is less than epsilon, right?
Yeah.
Which gives us that 1 over n is less than epsilon, which gives us that 1 over n is less than 1 over a, which gives us that n is greater than a. And we're done. Archimedean property. For any real number a you pick, I can find an actual number n bigger.
That's pretty cool.
Heard of lost K.
La la la.
Oh.
Well, you'll have to do it. Okay, that's time. So when you come back with your homework, you better have all of them done except for maybe 8 and 14. But I'll be here after school, so I can help you with those as well. So there's really no excuse. So let's get it all done. Let's get all caught up with homework. Let's finally move on with our lives. Okay.
That doesn't
What do you mean that doesn't sound good?
I said